All right, so let's start. So welcome the NIPS tutorials, and this morning we have the pleasure to listen to two experts on optimal transport. So Justin Solomon from MIT and Marco Couturier from Université Paris-Saclay. So the tutorial will be in two parts, 1 hour, then taking questions during the break, and then another 50 minutes or so. So please, Justin.
All right, thank you. I think I'm Hello, does that work? I don't think this, oh, there it goes, okay. Hi everybody, well it's a pleasure to speak with you today and to share with you thoughts about the area of optimal transport. Optimal transport is one of these areas of mathematics that has brought a lot of excitement to mathematicians over the last maybe century, and just in recent history has reached the stage where we really can think about plugging it into applications. So enabled by some developments both on the application side as well as in large-scale optimization and related areas, we can begin to think about optimal transport not just as an interesting area of study in measure theory or mathematical programming, but as a sort of application-oriented tool that really can make a pretty positive difference in some machine learning applications. So today, of course, we should begin by telling you exactly what optimal transport is. And in fact, optimal transport we can think of like a geometry for probability measures. And we're really going to dig into exactly what we mean over that over the next half hour as I introduce the basic ideas of transport to you all. And the history of optimal transport as a mathematical discipline reaches all the way back to the 18th century to Monge. If you jump forward a couple centuries after that, then in 1975, Kantorovich and Koopmans actually received the Nobel Prize for work related to this optimal transport problem. And since then, it's really evolved into an area that's brought a lot of excitement in the mathematical community as an interesting tool for analysis. But from a machine learning perspective, the reason that we're so excited about optimal transport is that really, obviously, the probability measures show up in so many different places and in so many different applications that are really key to what we care about in this discipline. So when we talk about using transport as a geometry for probability measures, there's so many different contexts that we can think of where that makes some sense. And here we've illustrated just a few out of the many that appear in the applications we've seen over the last 5–10 years of transport. Perhaps the most concrete application is on the lower right here, if we talk about color histograms. So let's say that I have two photographs. So here we have one that's largely blue and another one that's mostly orange. And I would like to compare these photographs, so have some notion of how similar they are. So in this case, the probability measure that we might talk about would be the collection of pixel colors, thought of as a histogram over color space. Similarly, if we talk about brain imaging, maybe we talk about brain activation maps as, you know, the probability distribution here would be, you know, the areas of the brain that get activated as some function over the surface of the brain. Or in bag of feature models, so for instance, if I look at a document and think of it as a bag of words, right, then now the probability measure that we would speak of would be the histogram over the dictionary, which is all of the words that appear in a document. And then what optimal transport will provide us is a tool for comparing two documents by putting a distance on that space. And then perhaps one of the most exciting applications that we've thought about certainly in the last few years will be in the generative modeling world, right? To understand if I have a generative model that's trying to sample from some distribution that's representative of something that I observe in the real world, and I have you know, a data distribution that's sampled, you know, collected from a data set, then I'd like to measure some notion of distance between the measure that comes from my sample and the data that I'm generating using my generative model. Of course, when we talk about optimal transport, it really is a geometric theory, and part of the way that we can understand that is the measures that we'll talk about today are supported on a geometric space. In particular, for instance, if we talk about the brain activation maps, then the piece of geometry that the measures are supported on would be the surface of the brain, or the color histograms maybe sit on top of RGB or HSV space. And then recently, methods like word2vec actually provide some geometry for the space of words, which is a little bit surprising and allows us to compare our bags of features in a reasonable fashion. The more abstract one might be if you take a look at this generative modeling problem, we could zoom in a little bit and understand that we have some distance between the data points that our generative model is sampling and perhaps the actual generative distribution that we'd like to sample from. and then we need some notion of divergence that measures how well we're doing. Okay, so today, Marco and I are going to spend the next 2 hours telling you guys both a summary of the discipline of optimal transport as a mathematical area and as a tool in optimization, but we're really going to focus today on how to plug it into the machine learning toolbox. And we'll see that in a lot of different applications, both thinking of optimal transport as a loss function as well as a tool for estimation. Notice that already in our slides I'm using this letter W here, which stands for Wasserstein, which is going to be the primary distance that appears in the optimal transport world. As a quick advertisement, if hopefully our goal today is to get everybody really excited about this new area, and if you can't get enough in the next 2 hours, then you can get it in a lot of different places throughout the next week at NIPS here. So in particular, on Saturday, we have a workshop on optimal transport and machine learning, which includes 7 talks from people all the way across the spectrum from mathematical theory to applications in the transport world, as well as 17 posters. It was actually really exciting reviewing and looking at materials for this particular event, because we really received quite a bit of really interesting non-trivial work here. And finally, if you'd like to see the slides, as well as a really great survey paper that was prepared by Marco, as well as our colleague, Gabriel Perret, you can take a look at this GitHub link that I have at the bottom of the slide here. So without further ado, let's dive right into the optimal transport problem and give you a flavor for the mathematics and the construction of this particular tool. So we're actually going to have 2 different motivating examples, and then I'm going to argue to you, at least at a high level, that these are very closely related to one another. So one of them is going to have to do with moving earth, in particular moving piles of sand, and the other will have to do with moving soldiers over a map. Okay, so the original optimal transport problem arguably appeared in 1781. It was posed by Monge, who's a mathematician, and what kind of one of the really funny things about if you look at his original paper in French, and unfortunately I do not speak French, but my colleague Marco does, is that he already was using the language that we use in machine learning today to discuss a lot of the optimal transport tools, namely this Earth mover's distance. But essentially, the problem that he was considering was all about transporting Earth. Here, Earth means, like a pile of dirt, from one place to another. So let's take a look at the situation that Monge was thinking about. In particular, let's say that I have a pile of sand, and I'm going to represent that using a distribution function mu here, right? So that's the red guy on the left-hand side. And there's sort of 2 dual ways to think about the blue function. Either it's a second pile of sand, or it's a hole that, whose depth is exactly has exactly the right amount of space to hold all of the sand in the distribution mu. Yeah? And my goal at the end of the day is to take mu and move it on top of the distribution nu. Now, of course, in the 21st century, we have a pretty simple solution to that, which is just to use electronic equipment. But back in the 17th century, the 18th century rather, Monge had to be a little bit more careful. In particular, the equipment that Monge had available to him was not a plow, but rather a shovel. So here, let's say that I have the distribution, mu of x, which is giving me essentially the height of the pile of sand at every point x. And now I have a shovel, and I have to do some backbreaking work, which is to scoop up mu of x and drop it on top of nu. So if we think about it, when we go through a process like this, where I'm trying to scoop up one pile of sand and drop it on top of another, implicitly, underneath all of this is sitting some function, t of x, which is telling me the destination for every point x. Right? So in other words, if I scoop up sand with height mu of x on the left-hand side, and now I walk over to the distribution mu and I drop it down at a particular point, I'm going to say that the destination of that point is t of x. And so there's some function t telling me a mapping from the source to the target, or in other words, where every grain of sand went. Okay? So now, of course, there's this process of scooping up the sand and dropping it back down. And I could measure the amount of work that I do in the process of transforming one distribution into another. Yeah? And in particular, if I take this one grain of sand located at x and drop it at t of x, then I can think of the amount of work that I did to move that sand across the line as proportional to the distance from x to t of x, which are going to encode as a function d. Okay. So in other words, the work that I did to transform or to move just one grain of sand is equal to the weight of that grain of sand times the distance that it traveled. Now, Monge has, his task is not just to move one grain of sand, but really to transform the red distribution into the blue one. And in particular, we need to add a constraint to our problem, which has to do with taking the entire red distribution and dropping it over the entire blue distribution. In other words, that the total amount of sand in mu ends up filling up that whole nu exactly. Okay? So let's formalize that a little bit. In particular, let's say that I take a set B on the right-hand side. And I could look at all of the grains of sand that get dropped into that interval B on the right-hand side. And roughly, what I'm trying to do is figure out all the different source points for a single target. And we can define that using this particular notation called a pre-image. So the pre-image of B is the set of all points x so that T of x is in B. So if you think about it, that's the set of all the points in the distribution mu that get dropped onto the interval B in the distribution nu. And what do we know? Well, we know that the total amount of sand there equals the sum over all of the sand that comes from all these different pre-images. Right? So if we're solving this Earth mover's distance problem, then I can sum up, the total amount of sand that was sent from A1, A2, and A3. And that should give me the total amount of sand in the hole located just within that interval at B. Now I can write that as a constraint like this. Now, of course, that interval that I drew for you, B, is completely arbitrary, right? I just drew some random line on the real numbers. And the reality is that I could choose a lot of different locations here. And no matter which one I choose, I need to make sure that the total amount of sand that reaches that interval B is equal to the sum over all the pre-images of the sand that's sitting on the left-hand side. Right? So remember, we have this function T of x, which is telling me how much, the destination for every point x under my picking up the sand and dropping it back down. And now I have a constraint, which is that T of x really pushes forward this distribution mu onto nu. And in fact, that's exactly the language that we use. So a different way to put that mathematically is that for all sets B on the right-hand side, the amount of sand in T inverse of B is equal to the amount of sand in B in the target, right? So in other words, mu of T inverse of B equals nu of B. And that's our constraint. And all this constraint is saying is that T must map the red guy onto the blue guy. And in the theory of optimal transport, we use slicker notation for this, but it's essentially just encoding that basic idea, which is that T must push forward the red measure onto the blue one, and we write that using this sharp operator here. Okay, now, there are a lot of different ways that I could scoop up one distribution and transform it into another, right? I mean, I could pick one up, I could walk from LA to San Francisco and back and then drop it back down, or I could try and do something a little bit more efficient. And of course, Monge in the 1700s was a pretty lazy mathematician, and what he wanted to solve was a problem that you can think of like planning, right? He wanted to minimize the total amount of work that he did scooping up mu and dropping it onto nu. And now we have all of the material or the machinery we need to be able to oppose a problem like that. So in other words, over all of the possible mappings T, remember T encodes the mapping from source to target of every grain of sand, over all the possible mappings that push forward mu onto nu, I'd like to minimize this particular notion of work, which really is equal to the mass, which is measured as mu, times the distance that it travels, now integrated over all of the source points x. And this is the Monge problem. Now, Monge posed this problem, but it took many hundred years to make progress on it mathematically. This is an incredibly difficult problem. If you think about it, there's a very sort of non-convex, messy constraint on the first line. The objective function looks like an integral, which maybe is kind of frightening looking. And so it took quite some time to make some progress on it. And actually, the progress came from a relaxation of this problem known as the Kantorovich problem. And now this is much more modern. This dates back just in the last 100 years. In particular, there's a monograph in the 1930s. Although this idea sort of was just in the air at that time. So in fact, Marco and I spent some time trying to track down a lot of the different early references that all appeared in the 1930s, 1940s. And it's a little unclear who wins for defining every one of the concepts that we'll talk about here. But the basic idea, the basic problem that Kantorovich faced, he was in Russia, and he wanted to move around troops. Yeah, so let's say that I'm organizing some kind of military exercise, and I have barracks, and then I have the front lines. And in particular, if we zoom into our map of Russia a little bit, we have some distribution of soldiers. So here I have 60 soldiers at one location, 90 at another, or 150 at a third. Probably we should multiply all these numbers by 1,000, but that's okay for our purposes today. But at the end of the day, we're running some military operation which has demands for soldiers in other locations, right? In particular, we have a demand for 120 soldiers, 90 soldiers, and 90 soldiers at these 3 locations on the kind of lower left. And the question is, how should I move the soldiers from the barracks to their final locations, right? What assignment should I give to each of these people in terms of where to start walking? And there are a lot of different ways to do that. So for instance, one thing you might notice is that we could take sort of a proportional split between our source and our target, right? So we could take all 3 barracks, divide them into 3 parts, and say, okay, this group goes to the first destination, this group goes to the second, this group goes to the third, right? So now, here this guy goes to the first place. We'll take another 18 of these folks and send to the second, another 8 into the third, and I could run the same rule, just a proportional split over all the different barracks. And this does give me some, plan for moving all of my soldiers to the final destination. But what do we notice? We got a lot of people moving in a lot of different directions, right? And some people, like the very unlucky gentlemen who start on the lower right and end up on the upper left, have to walk a very long distance. Yeah? And so, in fact, what we notice is that the naive approach here results in a lot of different displacements, and some of them are really expensive. And so the goal of Kantorovich was to find a cheaper alternative. So let's formalize that a little bit. So we'll go back to our original problem here, and now we'll drop the map and write it in a slightly different way, where we're going to take a table and write the rows and the columns as the sources and the destinations. Right? So here I've taken all of my barracks and written them as rows. And you can see we have 60, 90, and 150 people. And we have the destinations on the front lines as the different columns, which have demand for 120, 90, and 90 people. In addition, we can try and understand what this map is in a slightly less messy way by encoding it as a distance matrix. So here, the distance matrix gives me the distance from every possible barrack to every possible point on the front line. Right? So for instance, D1B is the distance from source point 1 to target point B. Okay, so now what are we going to do? Well, we can notice that the entire problem is described by the counts that are sitting on the left-hand side of the matrix on the left, as well as the cost or distance matrix on the right. So let's move this up here. So if we want to formalize the problem that Kantorovich was facing mathematically, what will we say? Well, essentially what we're missing are the question marks on the table on the left. Right, so we can think of the table on the left as telling me how many people go from each of the rows to each of the columns, and we're going to encode that using a new variable, P. Right, so P is a big matrix which is telling me how many people go from each source to each target. Now, of course, the numbers 60, 90, and 150 here aren't particularly important, so to generalize slightly mathematically, let's replace those with letters A and B. And now we have all the language that we need to pose the Kantorovich optimal transportation problem. Yeah? So in particular, what are our constraints on the transportation matrix? Well, we need to make sure that all of the soldiers leave their barracks, and we need to make sure that the front lines are all filled up. And for today, we're going to assume that we have a demand that's exactly the same size as the size of our source. In other words, we don't have like a surplus of soldiers or something. Although maybe briefly at the very end, Marco can mention how we might take care of that. So that can be encoded using these 2 mathematical constraints here, right? That if I sum over all the columns of P, then I get the source sums A. And if I sum over all the rows, then I get the target sums B. And what is the total cost? Well, if we think about it, it's kind of like the total amount of work that's performed by all the soldiers. We can measure as the total amount of soldiers moved from every source to every target times the distance they have to travel. Right? So this is kind of like the total amount of work that the whole military had to do in this particular exercise. So if we're solving our logistical problem, at the end of the day, what we want to solve is minimizing the total cost subject to P being valid. In other words, satisfying the constraints on the left-hand side. And that's exactly the Kantorovich problem. So if we take a look at our original problem here, we can solve this pretty easily because it's pretty small. And the solution's on the left-hand side. And one thing that you noticed here, there are sort of 2 features to see. Right? One is that we don't send military from every source to every target, right? There's some entries that are just 0 here. And the other thing to notice is that there are some barracks where, like, for instance, 30 people go to one destination, 30 people go to another. Right? Notice that this contrasts with the Manche problem that I set up for you, where everything at a source point x has to go to a target t of x. Okay, and there's our plan in action. So now that we have these two motivating problems, let's formalize things mathematically. So both of these problems we can think of as involving probability measures. Remember that a probability measure is a function that's positive and sums to 1. So here we can think of our probability measure like the function telling me where all of the sand is. Maybe it doesn't sum to 1, but it sums to the total number of kilograms of sand. That's okay. Or we can think of a probability measure which is telling me the locations of all of the soldiers on a map. But in addition, these probability measures are in a geometric space, right? The sand is getting pushed along a line here, and the soldiers are moving along a map of Russia. So now we can formalize the Manche problem as I've given you on this slide here. So we have a probability space omega, right? That's like the set of all possible distributions of sand. And we have a cost function c telling me the expense of moving sand from every source point to every destination point. And finally, we have two probability measures, mu and nu. Right? This is like the red distribution and the blue distribution that we saw before. Then the Manche problem from 1781, I think that apostrophe is hiding a little bit, is to find a map T from the source to the target, which minimizes the total cost, which is measured by the cost of moving from x to t of x multiplied by the total amount of mass, mu, which is moved from x to t of x. So Manche posed this problem, but of course it took quite a long time to make progress on it. And although the slide looks like it only took 6 years, in fact, I think it took, 206 years to really understand these maps T. And in particular, there's a really elegant result by Brenier, which shows that at least if your geometry is provided by Euclidean space and the cost function is the squared distance, notice this is slightly different from the original Manche problem, then you can prove that, in fact, the transport map T exists whenever mu and nu are absolutely continuous, and that it's the gradient of a convex function. It's a very nice object. Unfortunately, well, this is a really elegant sort of formalization of the problem and a really elegant way to describe the solution. Computationally, we'll see that it's quite hard to work with this description. And one of the main reasons is illustrated here, that this absolutely continuous condition is actually really critical. So for instance, let's say that I have a delta function, so like one really, really big pile of mass at one point for my function mu that I want to transport to nu. Well, then it's really obvious that I'm going to have to split that in half, right? And in particular, this is a simple argument to say that this map T doesn't necessarily exist for all possible probability measures, right? So there's a little bit of an additional condition that you need there. So now let's talk about the Kantorovich problem, right? We're moving soldiers around Russia. So now, instead of talking about maps, we're going to talk about measure couplings. And those are measures on the product of omega, or of omega in itself, that satisfy two constraints. And these are just like that matrix of probability values P that we talked about before. Remember that P satisfied two primary constraints, that it's rows summed to the source, and that it's columns summed to the target. And that's essentially the only thing that's encoded in this probabilistic language here, right? So I can think of there being a distribution over the product of the space in itself, right? So here, pi of ij might tell me the amount of stuff moved from I to j. And the two constraints that you see are just saying that we cover the entire source distribution mu, and that it gets mapped to the entire target distribution nu. So we can illustrate that using this image here, right? So if we have two one-dimensional distributions, mu and nu, those are shown on the two axes here, then we can think of a measure coupling like a function on a square, right? And essentially that function is tall if a lot of mass gets moved from that source to that target, right? So here, the red points are illustrating the pairs of points that are getting mapped to one another. And the important thing to note here is that there are a lot of different things that satisfy these constraints. So here, I think this is the sort of naive mapping that you can get from basically just multiplying mu of x and nu of y. Another mapping that turns out to satisfy the same constraints looks something like this. And over all of the possible measure couplings, the Kantorovich problem says to find the coupling that minimizes the total cost multiplied by the probability. Right? So remember that c of xy, you can think of like the cost of moving mass from x to y, and that gets multiplied by p of dx dy, which is the amount of mass that gets moved from one to the other. Right? So our unknown here is p, and our cost is c. Notice that although we're writing this using integrals, if you guys are familiar with linear programming, this is really just a linear program, right? The unknown here is p. It's getting multiplied and summed up in this integral, and that's your objective function. And the constraints are basically look like inequalities, and really mostly equalities plus a non-negativity constraint. Now, in machine learning, we tend to like probabilistic notation better, and you can actually write it in a very slick fashion as an expectation, right? Essentially, if you think of x and y as random variables that are distributed by this unknown distribution p, right? So p, you remember, is the thing telling me where every source gets mapped to. Then roughly what we're trying to do is to minimize the expectation of the cost over all of the possible couplings. Now, those of you who are familiar with convex optimization know that for every minimization problem, there's something that we can call a dual, which is a maximization problem that's going to achieve the same objective value and also can tell you something about how to solve the primal problem. And indeed, the dual of the transport problem is really elegant, and it's shown here. So roughly what you end up with, remember whenever you take a dual of an optimization problem, essentially you get a variable for every constraint, and you get a constraint for every variable. Here, our variables end up being what we'll call potential functions, and Marco is going to give you a little bit more intuition about that when he speaks later. And they get integrated against the distributions mu and nu, and they're subject to this constraint that the sum of phi of x and psi of y is always upper bounded by the cost. Right, so if you think about like what did we gain here, we gained that we have fewer variables, right? Pi sort of scales quadratically in the size of my problem. Right? There's a pi of x comma y, whereas there's a linear number of variables in the dual, but there's a ton of constraints. They're kind of complicated ones as they go. Okay, so I set out to describe the transport problem, and of course, we described two different transport problems, and on this slide, we've noted the link between them. Notice that if you have a solution of the Monge problem, this one where I want a map T of x, then that actually encodes some feasible solution to the Kantorovich problem, where I make a measure coupling that's very, very thinly concentrated on pairs x comma T of x. Right? So you can think of the Kantorovich problem as a relaxation of the Monge one. And one of the really exciting results in the theory of optimal transport is that for sort of well-behaved cost functions and densities, you actually, the inclusion goes the reverse direction as well. That if you solve the Kantorovich problem, hiding inside of the optimal solution is actually a map T of x under some assumptions on the distributions mu and nu. So these are very, very closely linked problems. So I'm going to conclude with my last little 3 or 4 minutes here with just a few more definitions. One of the really critical cases of the Kantorovich problem that we've already seen today is when your cost matrix is actually a distance on some geometric space. And then we can call that the p Wasserstein distance. So here, our cost is going to be distance to the pth power. And when we solve the transport problem with this cost, and we look at the optimal objective value, one thing you can check is that if you take the pth root of that number, it satisfies the triangle inequality as long as p is greater than or equal to 1. In other words, we really can put a distance on the space of probability measures that's lifted from this optimal transport problem. This is called the Wasserstein distance. One thing to note, our notation here, notice that we solved the transport problem. By the way, notice that this is still a linear program, even though I'm taking a pth power. The p is in the cost, it's not in the unknown. But that aside, typically the notation here is they do w sub p superscript p like that. The superscript p is because we're taking the pth power. The subscript p is because it's the p Wasserstein distance. I don't love this notation, but it's what we got. So it's just FYI. And the Wasserstein distance actually puts, now that it's a distance between probability measures, we can think of the set of probability measures as some sort of a manifold, right? As really a geometric space itself, a very high dimensional one. But here, now we think of maybe there's two distributions mu and nu, and the Wasserstein distance actually gives some notion of how far apart they are. And in fact, one of the really exciting developments in the mathematical theory of optimal transport in the 90s is that this notion of geometry is actually quite strong. For instance, what McCann showed is that there's actually an interpolating set of probability distributions that realizes that distance as the shortest path. This is called the displacement interpolation phenomenon. And if we take a look at the displacement interpolation, it already begins to suggest why this might be an exciting tool for machine learning, right? So for instance, on the left-hand side, I'm showing you the shortest path with respect to like L1, L2 distance between two probability distributions. So here I have sort of a Gaussian-looking distribution, the blue guy on the left, and then I have some other distribution, like a mixture of Gaussians on the red one on the right. And if we take the average between them with varying weights, what happens? Well, effectively, mass kind of teleports from one distribution to the other, right? One thing just kind of shrinks while the other one grows up. Whereas if I take the shortest path with respect to the Wasserstein distance, as shown on the right-hand side, you can see that the mass actually slides along the x-axis. Right? This gives some intuitive notion of the shortest path from one distribution to another that sort of lifts the notion of shortest path between points that's sitting on the x-axis beneath it. And of course, we can extend that to problems like averaging things between things with different weights. So here's a figure from one of our graphics papers recently, where I have three probability distributions. Naturally, they're a cow, a duck, and a torus. I'm used to speaking to the computer graphics community. And these probability distributions are kind of like level set functions. And I can interpolate between them using the Wasserstein distance. And what happens is the mass moves along shortest paths in space, and it gives you this, this interpolation here. So you can see that really the features of these different shapes are interpolated from one to another. Okay, so what's our state of affairs so far? So I've posed to you two different problems, right? The Monge problem and the Kantorovich problem, both of which are really interesting optimization problems which actually give rise to an intuitive and interesting distance measure between probability distributions when they're supported over a piece of geometry. I know that's a lot of math words. Hopefully that parses by now. And what's missing? Well, there's sort of two natural questions, right? Well, the first one, you know, if I want to compute a distance like L1, L2, KL divergence, there's just some formula for it. But if you think about what I just gave you in transport, it's actually now kind of expensive. I have to solve a big linear program, right? So the first question we have to ask is, how do we just solve the optimal transport problem efficiently? And that'll be the topic of what Marco tells you about next. And that was really the focus of research in sort of applied optimal transport up to about 2010. And then we had all these exciting developments for fast optimal transport solvers. Our next goal was to use transport and incorporate it into larger machine learning pipelines. In other words, to use optimal transport as sort of a modeling tool that can be plugged into, for example, loss functions and other you know, things that we know and love in the machine learning world, and really not worry about the optimization problem as much as using it in an effective way in a modeling fashion. So if you think about it, what's missing for that second piece is not just computing the transport distance, but also taking its gradient with respect to the input distributions. So with that, I'm going to hand it off to my colleague Marco here, who will tell you about how to compute transport in practice. Good luck.
Okay, great. So, so indeed, so Justin has hopefully convinced you that this Wasserstein geometry is a bit special. It is very natural for probability distributions when you're on a geometric space. We had a few slides, a few nice pictures, you know, with those displacement interpolations and barycenters of shapes. The question that I would like to address now is actually what happens on the computational side. Is this very easy, very hard? And so we're going to, I will show you a list of cases where we will gradually move from the very easy case, where transport is actually can be computed almost in closed form, to things which are a bit more complicated. I will introduce a regularization that has been around for a few years now, and which has proved quite effective in a wide range of problems. And then I will address the very last point that Justin made, which is, okay, once we know how to compute transport, isn't the real question rather how we can differentiate it here? Because basically machine learning is mostly about gradients, setting a model, computing a gradient, and then just doing gradient descent. So if you want to use transport in machine learning setting, you have to be able to differentiate it. So there are actually three cases which are relevant for optimal transport. And the first one is the discrete to discrete case. So I have two probability distributions which are essentially point clouds, weighted point clouds. The second one is the one where I would like to maybe transport a discrete set to a continuous measure. And this is a bit more reminiscent of what Justin showed in the very first slide when he was talking about generative models. Sometimes you want to make a transport between continuous densities or a manifold onto data. And then the last case, which is about the continuous to the continuous case, is mostly of interest for statisticians. So what is the state of affairs in those three problems? Where I think it's fair to say that the discrete to discrete case has been around for about 50 to 60 years. So there's been a lot of energy spent on trying to find good solvers for that. I will show you, I will essentially talk about two solvers, the network flow solvers and entropic regularization. The other two cases, the semi-discrete and the continuous case, are really up for grabs. I mean, this is really something we have just started studying these problems. There's been a tremendous progress in low dimensional spaces, which are of interest in graphics, for instance. And also in the continuous to continuous case, we have now a few stochastic optimization algorithms that seem to work, but I would say that this is still a work in progress. So we'll be mostly focusing on the first case, discrete to discrete, or so let me just mention the very, very easy cases. So if you talk to a statistician, very often to a statistician, the Wasserstein distance is essentially a distance between univariate distributions. So suppose I am in the univariate case. Sorry, there is Larsen. So I'm in a univariate case where omega is equal to r. The cost is a function, is a translation invariant cost function. I'm making very few assumptions apart from the fact that C is here convex. Then we have a closed form solution for this optimal transport problem. So let me just, rather than looking at the formula exactly, let me just walk you through how to get the solution. Well, suppose I have my two measures, mu and nu. I compute their CDFs. I compute what is known as the quantile function of those measures, basically the inverse of the CDF. So here I've just taking the transpose, if you want, of those two curves. And then the Wasserstein one distance between those two measures is just simply a norm between those two quantile functions. So for a statistician, basically Wasserstein is a bit like shifting away from a density onto a quantile function representation for your data. The second very nice example and simple example is the one with Gaussian measures. So as usual, for many other geometries, we know that Gaussians are well behaved. Well, it's also the case here in Wasserstein. And let me just give you an intuition of what happens. Suppose that I have two Gaussians with a mean and a covariance matrices which are known. Then I can also compute in closed form the Wasserstein distance between those two Gaussians. And what the distance looks like is basically, it decouples, it's a distance between the means, the standard Euclidean distance between the means, plus a distance that only depends on the covariance matrices. And that distance is known as the Burrs metric. And it's been quite well studied in the world of geometry for positive definite matrices. What is also interesting is that in this particular case, the optimal map, the one that Justin was mentioning, the Monge map, is actually known. And it's a very simple map. It's a linear map. And what it does, and let me just show you a bit here on this slide, it will just take a point in the support of the first density, map it linearly, and this point will be transported to a point in the support of the second density. And what is really nice about this example is that this transport map here is the gradient of a convex function. Well, why? Well, because if you look at the matrix A as the way I've defined it on the bottom, well, you can very quickly check that this matrix is positive definite. And so what we get is a very nice illustration of Vognier's theorem, which tells you that the optimal transport between two densities, when you consider the Euclidean cost, must be the gradient of a convex function. And that convex function is here in this parabola. So away with the very simple cases, let's just start using data. So suppose we have 2 points, and I have this geometric setting, so I can compute the distance between x and y. And now suppose that I lift my perspective and I don't look at those points as just merely points, but as Dirac masses. So I somehow lift the space of my points onto the space of Dirac's on those points. Well, a very nice feature of optimal transport distances is that by doing this lifting, I'm not changing anything. By this, I'm saying that the Wasserstein distance between the two Dirac masses is actually, if you just walk through the computations, the same thing as the distance between the points. And this is a nice feature because this is not a feature that we would get, for instance, with other classic geometries for probability measures, because we would probably, if you just compute the Euclidean distance between two Diracs, then you have something that's not very meaningful. The next step and the next natural generalization that is interesting is that when you have 2 point clouds of the same size. well, then I'm not going to go through exactly the details, but if you just write out exactly the counter of each problem in that case, you will recover the linear assignment problem. So whenever you have done optimal assignment, Hungarian algorithm, etc., well, basically you were doing optimal transport in disguise. So this optimal assignment problem is optimal transport. And actually, you can even go further and with this analogy and say that the optimal assignment is basically equivalent to the Morse problem. So what we will be doing in most applications is a bit more general than just point clouds, uniform point clouds of the same size. That's too much of a constraint. What we want to compare is two empirical measures, or two discrete measures. And so I will be using a lot of those two notations. The red measure is a sum of AI Diracs on the xi's, and the blue measure is a sum of pj's Diracs on yj's. So if you look at those two measures, they are entirely characterized by two objects. On the one hand, I have weights, A and B, and I have locations, xi's, yj's. So the locations can be pretty much anywhere. I don't really have any constraint on them, but to make things a bit coherent, the weights must sum up to 1, right? I need to be comparing two probability distributions. So in this drawing, the length of the sticks here, if you sum them up for the red measure and if you sum them up for the blue measure, you should get the same thing. You could also, of course, see this as a very simple abstraction of the problem that Justin showed about soldiers. Here, basically the length of the sticks is the size of a barrack, the cross is the location, and then you have the front line with the location that you want to send the soldiers to. So the point is how to compute optimal transport. Well, as Justin probably gave you a very strong hint, well, what we boil down to, what this all boils down to is a linear program. And the program is entirely defined by two things. The first thing is geometry. This is a crucial point in transport. And geometry is entirely encoded by this cost matrix or distance matrix mxy. It's just a pairwise distance matrix of size n times m. And the other thing that we need to encode is transportation. And transportation is entirely encoded by the marginals a and b. And so I'm going to use this notation u of ab for the set of all matrices in nm such that the row sums are equal to a and the column sums are equal to b. Here you should see immediately the analogy with the couplings, the continuous couplings notation that Justin presented earlier. And then with all of these two elements, we can define the optimal transport problem. That's basically the minimum of a set of all matrices that satisfy those marginal constraints of the cost, the linear cost between P and Mxy. So as Justin mentioned, this problem has a dual. So here it may be easier to see what this dual looks like because we've been mostly taught about duality with finite dimensional optimization problems. So here in this problem we have n times m variables, and we have, it's not maybe obvious from the start, but we have n plus m constraints. Why do we have n constraints? Well, each of the AIs encodes one constraint, and there's n of them, and each of the BJs encodes one constraint, and there's m of them. So we have a problem with nm variables and n plus m constraints. Duality tells us that we will have a problem with n plus m variables and nm constraints. And that's what the dual looks like. And without getting too deeply into this primal dual relationship, let me just show you what the optimal solutions look like. Let me just plot them. So suppose that I have a blue cloud of point and a red cloud of point, and I want to basically transport the blue to red. Now, what I can do is run this optimal transport solver on the primal that will give me this matrix P, and here I'm just representing P as in those values where it's non-zero. So basically, if I have a line, it means that from one source to one destination, there is a transfer of mass. The dual problem, on the other hand, gives me a different output. It's not about what it gets transported, it's about giving me a single real value for each of the blue points and each of the red points. And here for commodity, for convenience, sorry, I've plotted those values as a heat map. So here what you can see is that on the blue measure, on the circles basically, I have a few values, and they seem to be hovering above 50 for the lower left corner, and then 40 in the middle. And for the red measure, those values are kind of negative. They're going down to minus 40, except for one point which is up on the right there, and it's pretty high relatively, and it's about 0. And what you can actually interpret those values for is basically prices. What those values tell me is how expensive each of those points is when I need to transport the red measure to the blue measure or vice versa. So what what this tells me somewhat is some sensitivity analysis, some kind of differentiability point of view, telling me how costly, for instance, the lower left point is. And so if I had to actually remove one point from the blue measure, well, intuitively you can immediately see that you would want to aim for the lowest left point or the upper right point, but this is actually rigorously quantified using the dual problem. So these are the two problems. So now what about solving this problem? So that's I guess the main challenge here. Well, if you just take a step back, what we have is a linear program. We have a set of equality constraints and non-negativity constraints. We have a cost vector. Here it's a matrix of size nm. And the goal, of course, is to find this optimal transport, meaning the matrix in that set which has the smallest possible dot product with mxy. So there are a lot of solvers to address this problem. And some of them heavily rely on some properties of the metric space. So for instance, if the metric is the Wasserstein-Whiten metric and you are on a graph, I mean, there's a list of several cases where we can relatively efficiently compute those values, the transport. But if you are in a very generic setting, and this is mostly the case for us in machine learning, usually we don't really like to make strong assumptions on the metrics, on the spaces, or the cost that we're doing, then you're basically stuck with linear programming, and you're stuck with some solvers in linear programming. There's a few of them, but let's say that most of us would use a mean cost flow solver. And the problem in that case is that the cost for those to solve that problem is actually super cubic. So from a OR optimization perspective, this is actually very cheap. We have a problem with nm variables, or let's say n squared to simplify, and I'm telling you that you can solve it with n cube effort. So that doesn't sound very bad if you compare this with the complexity bounds of linear programming. So we have a very specific linear program here. However, in applications, if we really want to use it not just once and not solve optimal transport once, but several times, millions of times, because we want to compare many, many distances, then this is prohibitive. So that's one first problem. The second problem, I think it's particularly important for us in machine learning, is that if you rely on linear programs in your data pipeline, well, you have to know that the solutions that you get are unstable. Why? Because basically, inherently, linear programs look for vertices in those polytopes, and so you can very easily change from one vertex to another by just perturbating a little bit your cost function. So the problem is not so much that sometimes you will have an infinite number of solutions, because this actually never happens, but the problem is you jump around from one vertex to the other, and this makes your Wasserstein distance not differentiable. And the non-differentiable losses are a bit tricky to play with. They usually pollute a bit your optimization algorithms. So what we want is something that's faster and scalable, and something that can be maybe differentiable, hopefully. And one very natural approach to solve this problem was proposed a couple of decades ago by economists that actually had to deal with the results of those linear programs that were not very meaningful. And they proposed to regularize. So as usual in machine learning or statistics, whenever we have some problem that's a bit ill-posed or unstable, we just regularize the solution. And the very natural regularization for this problem is entropy. And by entropy, I just mean the classic Shannon entropy here. So let me just first give you an intuition of why and what happens when you do this. Well, think about this transport problem. I'm transporting this univariate distribution to another, mu to nu. Well, here, because I have a VGA projector, not an HDMI one, I mean the HDMI port, you can barely see the solution of the regular optimal transport problem, the original one, the one with gamma 0, the one on the left. What this tells us is basically that optimal transport in this case, Kantorovich problem is like the Morse problem. We recover something that's basically a map that tells me where the mass at each point x in the measure mu goes in the measure nu. Now, if you add this entropic regularizer, you're actually moving away from the Morse perspective. Not only do you want to have something that's more relaxed as Kantorovich, but you want something that's as fuzzy as possible within the, and you don't want to change too much the cost function. So if you're able to take a probability distribution coupling that's a bit more fuzzy, but that doesn't impact too much the cost, this is where you will be heading for. And of course, if gamma goes to infinity, what you eventually find is just simply the product of the marginals. This is the very naive coupling that we can study whenever you're given two marginals. So this is basically for the intuition. The second thing is, From an optimization point of view, something is solved here by this regularization because the regularization is strongly convex. So basically, entropy is a one strongly concave function. So minus gamma times the entropy will give you a gamma strongly convex regularizer. So the problem is has now a unique solution. So I can go on and write this P gamma is the argmin of this regularized optimal transport problem. The very nice thing about this optimization problem is that it's very simple. If you just write first order conditions, you get that necessarily there exists a vector u of size n and a vector v of size m, non-negative vectors, such that the solution factorizes very well. It factorizes as a diagonal matrix times a matrix K and a diagonal matrix. And that matrix K is basically a kernel. I'm writing it as K because it's the element-wise exponential of minus the distance. So if the distance is a squared Euclidean distance, this is a Gaussian kernel matrix. So how do we get there? Well, it's just a very simple calculus exercise. You just write the Lagrangian of your optimization problem. So the Lagrangian will contain the objective on the left, this is the green, and it will contain the two Lagrange multipliers for the equality constraints on the blue. You just take the derivative for order conditions, and this gives you the fact that necessarily the solution factorizes this way. This is a well-known result. So now we have to re-inject this formulation in our constraints. So what we know is that this matrix, diagonal times K times diagonal, has the right marginals. So let me just break this down for you. It is diagonal K, diagonal V times M1 is equal to A, diagonal V, K transpose diagonal of U times 1 is equal to B. So let's simplify this a bit because there's too many diag signs there. So diagonal matrix times the vector of 1s is just a vector, of course. So you just remove, get rid of this. Now, multiplying a diagonal matrix times the vector KV here, or K transpose U, is the same thing as taking element-wise product of the two vectors. So the element-wise of product of two vectors is equal to a vector. The element-wise of product of two vectors is equal to another vector. Let me just summarize. U must be equal to this A divided element-wise by KV and B divided by K transpose U. And what you get here is a set of nonlinear equations that characterize the solution. Of course, those nonlinear equations do not have a closed form. You cannot just give me U and V that satisfy this. But there is, however, a very, very simple algorithm, very naive one that anyone here could come up with, and which is to simply alternate between these two steps, these two update steps. And this is like a fixed point algorithm. It's a very simple algorithm. There's no gradient descent involved, nothing. It's just alternatively just update U and V. And this is called Synchron's algorithm. And it's called Synchron's algorithm because Synchron was the first to prove that it converged, but actually it's much older. It was proposed in the 30s and it has several different names. It's an algorithm that's very well studied. We have linear convergence rates which depend essentially on the matrix K, on the entries of the matrix K. There's also a very nice paper at NIPS this year that provides a different perspective on this convergence. And from a programming point of view, what is very, very nice about this algorithm is that it's 3 lines. So if you compare 3 lines of just coding with maybe a few thousand lines of coding for network flow solvers, this is very, very convenient. And the other thing is that this is, of course, a very simple algorithm. So we are just using matrix products. And matrix products can be very easily parallelized on modern hardware, including GPGPUs. So this is a very attractive feature. And then the last thing that I would like to mention, and which is basically propelling many of the applications in graphics, and some of them will be presented by Justin, is that the multiplication by a kernel doesn't necessarily need to be quadratic. It can be a bit less than that. So let me just walk you through a bit the Synchron algorithm. So just to make sure that you're convinced that this is a very, very simple algorithm. The Synchron algorithm has 3 inputs. We have A, B, 2 histograms, and K, this is the geometry of the problem. We just start with any initialization for V. We just multiply V times the matrix K. Element-wise division, we get a U. That's a vector of numbers. And then we're just going to flip one side to the other, and then I'm just going to update progressively and incrementally those two vectors U and V's. Of course, we could just do this until basically we have a convergence, and we reach the values that we wanted for those U's and V's. So this is a numerical algorithm. Now, how do I reconstruct the optimal transport matrix? Well, you remember for this, after L iterations of my algorithm, I could get a nice approximation of the transportation matrix. What is also nice is that if I want to evaluate the cost of that transportation matrix, then again, this is only a matter of taking matrix vector products. And this slide, I hope, has maybe given you the intuition that we're doing something a bit naively if you want to run Synchron on many histograms. Imagine that I want to compare several pair of histograms. Then, of course, rather than doing this for loop, I should do it basically using a matrix fixed point iteration. So this would be basically my matrix fixed point iteration. So I can broadcast basically the computation of maybe 10,000 distances between 10,000 histograms in parallel using a big GPU. So that's really the main point about this. So I'm going to not elaborate too much on speedups because I'm a bit uncomfortable comparing the network simplex with the Synchron solver because we're comparing with oranges and apples. But let me just tell you that if you are fine having a transport that is a bit blurry, then you can very easily have speedups of maybe 1 million times faster algorithms by choosing this Synchron regularization rather than the DLP. Let me just very simply say for people here in the audience that are interested in optimization that you can regard these Synchron iterations, which seem a bit magical here in my slides, simply as block coordinate ascent on the dual of this regularized optimal transport problem. So the transport problem, regularized optimal transport problem has a dual, which looks a bit like the Kantorovich dual, where if you just run a very simple algorithm on that, block coordinate ascent, you get Synchron. Let me just also clarify a relationship between the Synchron and another very popular distance for probability measures, which is known as MMD. Well, here I flipped a bit the slide. If I just take the value of the objective of the P star, the solution of the optimal transport problem, then I get the Wasserstein distance. This I think we have all understood. Now, if I take the value of this cost, but at P gamma, the regularized solution, I get something else, which is an upper bound on my Wasserstein distance. And if I actually go a bit further and let gamma go to infinity, what I recover is this very simple coupling that Justin mentioned. And actually, it turns out that these three quantities are very intimately related because I can very easily define an important quantity known as the MMD here by considering this naive coupling, the AB transpose coupling. And the only thing that I need to take care of is some normalization issues to make sure that this is equal to 0 if the two, if I put as an input mu equals nu. But then what you get is basically that this Synchron distance interpolates very naturally between those two quantities, between the MMD and the Wasserstein distance. So somehow this regularization strength gamma tries to combine the best of two worlds. So now let me just finish with the idea that Justin conveyed earlier, which is now in machine learning, we're not just concerned with computing this Wasserstein distance. I hope I have shown you I've convinced you that we have nice algorithms to do so. What we want to do is be able to differentiate. And that is, by this I just mean, what happens if I just add a small perturbation to my weights, and I would like to predict what the Wasserstein distance will look like. I would like to have a gradient. And the same thing applies for locations. What happens if I just wiggle a little bit the locations? What happens to the Wasserstein distance? Well, it turns out that if you just look at the theory of linear programming, there is a very simple sensitivity analysis there. So if you just think about the weights, what we have, if you just use the dual formulation of optimal transport, you have a max over a set of vectors of weights A and B's, and then you have those alphas and betas, which are the dual variables. What we know is that this function, as a function of A, is actually a convex function. It's a maximum. It's a convex envelope of a set of linear functions. And so as a result, the Wasserstein distance is convex as a function of the weights. But if you take the linear program, unfortunately, this is a non-differentiable quantity. So one of the nice and attractive features of the Synchron algorithm or regularization is that this yields, if you just add this small gamma here, you have something that's differentiable. Now, in some of the problems that we will be facing, we would also want to change locations. So this we call the Lagrangian perspective. So in that case, it's a bit more tricky. Because first, locations and spaces and metrics on those spaces are not, it's not so clear what metric is you should use. So if you fall back to the very simple example of Euclidean distances, then we have some machinery there. So the Wasserstein distance as a function of x and y, the locations, is this minimum over this transportation matrix P of a quadratic function of x. So basically, it's a piecewise quadratic function of the inputs in this case. So this is unfortunately not convex. But what we know is that we can linearize things. And when we just linearized directly using the non-regularized formulation, then we have some kind of upper bound that we can minimize. This is a bit, if you know about this, it is reminiscent of the k-mean step, the centering k-mean step. With regularization, we have actually a gradient, and that this is useful. Let me just conclude my section with something I think which is infinitely more simple, and that many of you here will probably appreciate, which is that what we're actually selling now is, rather than using all those sensitivity analyses that I provided you earlier, you should just see the synchron algorithm as a black box that takes as an input a lot of things, weights, A, B, locations, X, Ys, and then you just program a function that computes the distance matrix, MXY. You just take the exponential of minus that matrix, and then you just see synchron as a loop, and you stop that loop after a certain number of iterations, and you output the quantity that you want. And I think that it's really not a surprise to anyone now that this really looks like a neural net, and that you can actually differentiate this quantity WL with respect to any parameter that I've just provided here, because synchron's algorithm is a differentiable function. Every step of synchron is differentiable. We wouldn't get this with a linear program solver, of course. So this idea was used very recently. So I can trace back three papers in 2006 that used it. And so this has been also propelling a lot of the innovation of solving optimal transport problems. And not only computing the optimal transport, but also just simply injecting Wasserstein distances in your optimization problems, more advanced optimization problems. So this closes the second half of this first session. So I think we will have a break, and at the same time, if people are interested, you can ask questions. So we can take questions from now. Sorry? I guess. I think if you have a question, you can walk down the aisle. There are some microphones.
Hi. My question is, how well can you estimate the Wasserstein distance by sampling? If you want error epsilon, how many samples do you need?
Oh, this is a very good point, and I have avoided a bit this question in this tutorial. There is a big body of work that exists that is quite pessimistic, in the sense that if you want to really estimate the Wasserstein distance, and what you have access to is only, if you want to estimate the Wasserstein distance between two continuous distributions, and the only thing that you have access to is just samples, then let's say if you're in dimension D, then the error that you're making is basically decreasing as 1 over n to the power 1 over d. So it's a very bad regime. However, I think I take this observation as an additional motivation for regularization, basically. So if you follow this slide, what I was showing here is that this synchron approximation is somewhere in between MMD and Wasserstein. And basically, what I believe is interesting in this is that we are trying to come up with something that does a bit of optimal transport, that tries a bit harder at actually mapping things optimally, but not too much to avoid these overfitting problems and the fact that we have bad sample complexity. So, yes, yeah, and the dimension is so.
Yeah, when the dimension is low, it's not such a bad.
Yeah, of course. When the dimension is low, it's not a bad problem. But when the dimension is high, we need to regularize. So basically, my point of view is that Wasserstein distances and the linear programming framework that was defined in the 50s for that is not well suited for data. It works if you have observation, but not for random data. And so you have to regularize a bit more.
Thank you.
So thanks for the tutorial. Can I ask what the link is between the distances around Rao, Fisher, the distances, so basically the information geometry, typical distances, and optimal transport?
So it's an excellent question. So the first, I think the first remark, very simple remark, is that one is assuming or taking into account a lot more. It's asking a lot more from you. So optimal transport is basically asking you for this whole geometry on the base space, and it's going to exploit it as much as it can, because it's going to put it in this optimization problem. Whereas information geometry is completely agnostic, right? So that's from the start, I think they're completely different. sometimes they seem to result in things that look a bit alike. So for instance, if you look at the information geometry of Gaussians, it's not the same thing as Wasserstein, but you certainly get some nice interpolations between two Gaussians in Kullback-Leibler, for instance. On the other hand, I think that because you're using this knowledge, you're bound to get very different results when you will move on towards higher dimensions. And this is what we observe immediately when we play with our shapes in 3D. All of the applications where we do shape interpolation are completely impossible if you would use the Kullback-Leibler divergence. So that's one. And then my last comment is that actually if you use regularization, interestingly, you can actually re-inject a bit of information on geometry in there. Because if you look at the primal regularized optimal transport, I think you should recognize a linear term minus entropy, and that's just a Kullback-Leibler divergence. But it's a Kullback-Leibler divergence in the space of couplings. So somewhat we are mixing a bit both.
So just to be clear, which one of the two uses more knowledge or more information?
Oh, of course it's a transport. Because if you have no knowledge with transport, there's nothing you can do. If you don't have a prior geometry, there's nothing you can do. Information geometry assumes absolutely nothing about the geometry of your base space.
Thank you.
Sorry, just going to follow up on the information geometry. So is there embedding of like information, is there any kind of compatibility of information geometry, like an information manifold into?
No.
No?
No.
Okay,
Actually,
so it's just incompatible.
It's incompatible, and there are very strong results that tell you that actually you cannot embed optimal transport distances in like convenient Hilbert spaces, for instance. There's no way you can find, for instance, an embedding for measures in some RKHS or any Hilbert space, such that the Wasserstein distance between those two between the two measures is equal to the Hilbert norm between the embeddings.
Right. What about the other way, like embedding a finite dimensional information manifold into an infinite dimensional?
So here's one very simple case.
Yeah.
If you take the total variation distance,
Yeah.
okay, well, it's the optimal transport distance with the cost, which is basically equal to 0 if x equals y and equals to 1 if x equals y. So that's simple correspondence. So basically, total variation is the very naive case where you assume nothing on the distance except that 2 points have distance 0 if they are identical and 1 if not.
Okay, cool, thanks.
I just wanted to clarify, did you say that when you're computing the gradient that you were back propagating through the sinkhorn steps?
Yes, okay. Well, this is one way to do it. What I was basically saying is this part was more mathematically, I would say, rigorous. But being mathematically rigorous, it actually hides a lot of things under the carpet, such as, did we really converge? Did the sinkhorn algorithm converge? So rather than being mathematically rigorous, but actually when you are at implementation step, you have a problem that the algorithms didn't converge. Right. You can actually be more engineering-minded from the start and just say, okay, this sinkhorn algorithm, in the end, it's just a black box that kind of approximates optimal transport efficiently. Right. I don't want to go all the way down to compute the exact optimal transport because I know that in most applications it doesn't really make sense, especially in machine learning. And so I would just do this. I would just backprop through sinkhorn. And there's a few papers that are being doing this.
Thank you.
Hi. So can you tell us a little bit more about the entropic regularization? Like, does it force points that are close in one measure to be transported close in the other measure, or not necessarily?
Well, it's completely, there's a slider there. There's this gamma, and it interpolates continuously between the solution of the optimal transport. So the optimal transport is what you described. It's basically, it's not just pushing points which are close to each other to be mapped. It has a more global perspective, right? It's not just I will just move towards my nearest neighbor. Because if I move toward my nearest neighbor, maybe someone else cannot move towards it and has to do a very, very long walk towards another point which is very far. And so maybe that might not be globally optimal. So if you want, when you are doing optimal transport, you're trying hard to make everyone happy, but they are all bound to move together and land together at some prescribed locations. Now, if you increase this gamma, what you get is what Justin showed in the very first slides, where when you solve this barracks to a frontline problem, you might do this very naively and just say, I'm going to divide proportionally to what's going on. So the barrack is just divided into 3 groups, the second is divided into 3 groups, etc. And then you just send everyone. And that's gamma goes to infinity, and that's equivalent to MMD, basically.
So do you think it still makes sense, or it's just for the optimization to help it?
What do you mean exactly by that?
So do you think it's like just complexifying the problem, or it's actually doing
yes,
something
you have an excellent
meaningful?
point. So this goes a bit back to what I was answering a bit earlier. To me, it's a way to robustify it a bit. So if you look at the optimal transport matrix, it's a very sparse matrix, and it basically says that guy goes there. And if you just perturb it a bit, all of a sudden maybe that guy will go there. Whereas if you add entropic regularization, then you will continuously move between those two assignments. You would say, okay, in the beginning I send most of the mass to this guy, but a bit to this one, and then I would just shift around. So it has this property of making things more smooth, more robust, faster from a computation perspective, and also, and this is not yet proved, but we see it empirically, also better in terms of sample complexity, this statistical regularity. If you really want to approximate the Wasserstein distance between two continuous densities using samples, you're basically overfitting your samples, and you're very far from what the actual Wasserstein distance would be. Regularizing is basically making you a bit more careful, and this seems to be working.
Thanks.
Hi, I have two questions. Maybe you covered this during the lecture, but is a regularized Wasserstein distance a proper distance?
Oh, that's a very good point, and we won't have the time to cover it today. Not really, but there are ways you can modify it to make it somewhat like a divergence. Okay. So there's been interest from people in information geometry. Mm-hmm. Actually, I should have answered that earlier. There are some recent works from the information geometry community that try to provide some kind of information geometric perspective on optimal transport, and in particular take the effort of taking this regularized framework and turning it to a divergence, a proper divergence, with nice properties like convexity and things like that.
Yeah, the other question, maybe related, is that if you take this convex case and send this gamma, the regularization parameter to 0,
yes,
then is the gradient, does the gradient converge to this one of the subgradient of the unregularized
yes, it would. Yes.
Stein?
Yes, it would. Yeah. Yeah.
Okay.
It will be there somewhere in subgradient, yeah, subdifferential.
All right, thank you.
Hey, my question is a little bit more simpler, is relating to the programmer's view of the sync-on algorithm. What happens if this algorithm for some manifold doesn't converge, or we end up overtraining it?
We end up what?
Overtraining it, like training it for more iterations, since this is an iterative algorithm? No,
this is a very good point. It's not obvious how, I mean, you can monitor the progress, of course, of the synchronous algorithm, so this is easy. It's a good question. I mean, how do you set this L? So it seems a bit like if you choose a small L, you're doing some kind of early stopping regularization as well. It's a very good point, and we don't really have a satisfactory answer now, apart from monitoring basically how close you get to the solution. The other thing that I didn't mention, and I should be a bit more clear about this, is that you can get numerical problems when the value of gamma is too small, and so there are some workarounds for this. And why does it have to happen? Well, if you remember, gamma very small means that you're taking exponential minus of something that becomes very huge, and the numbers there converge to 0, and then there's the algorithm doesn't converge anymore. So if you're planning to use synchron, I can foresee that at some point you will have some nans, and you might ask yourself, where do they come from? And they probably come from the fact that some of the gamma values are too small, and so maybe you have to, there's a few tricks and hacks that you can take to correct that. One of them is threshold distances and things like that. But so all in all, choosing the right number of iterations, choosing the right regularization strength is not an obvious problem.
Thanks a lot for a great talk. I've got two questions. The first one is, would you say that on average, it's kind of like morally equivalent to do trust region optimization in KL space or in Wasserstein space?
Trust region optimization but you mean I'm optimizing on the space of probability measures?
Yeah. And because of the HWI inequality on one hand and because of transport inequality on the other?
No, I don't think so. Yeah, so the inequalities are fairly loose. And so, of course, they exist. But if you actually run this, you will get very, very different results if you minimize with the Kullback-Leiber loss and with the Wasserstein loss. I mean, radically, I can very easily cook up examples where the solution, where if I put a KL somewhere and replace it by a Wasserstein, you will get completely different results.
Okay.
Especially in low dimensions, 2D or 3D shapes, it's very obvious.
Thanks. Thanks. And my second question was, to the best of your knowledge, has there been some applications of gradient flows to neural networks?
Oh, yes. So actually, there's a very, very nice paper that I'd like to advertise by Hashimoto and other colleagues at MIT that actually uses a bit of, well, it's not exactly gradient flows, but they use the Wasserstein loss in a temporal setting, so in dynamic settings where they estimate RNNs using a Wasserstein loss. There are some papers on gradient flows and numerical and computational methods for Wasserstein gradient flows, and actually there's one in our workshop this Saturday. So if you come, I think Charlie Fromner has a paper on that. So I think we have to start again. So I'll let. Wait,
can I ask just one more question?
Maybe later.
Okay, sure.
Because we're scheduled to start again.
Yes, appreciate it. I think you can just close it. Cool. Perfect. All right, y'all. I'm back. It's such a pleasure to talk to you guys today and to be the first person, because it means that Marco's on the hot seat for all the questions here, which is really great for me. I've learned something today about how to organize a tutorial. Anyway, so today, now that we have the basics of how to optimize for the Wasserstein distance, hopefully, at the very least, what you've gotten out of Marco's talk is that at least in the last 5–10 years, we've had these huge developments in computational optimal transport that take this problem from kind of a theoretically interesting but computationally really heavy thing to actually a pretty practical tool, right? And that includes introducing regularization, that includes just fast techniques for minimizing this cost function very quickly. And now, especially for a person like me who's a little bit more application-oriented, one of the really exciting things is that we can view transport maybe not as a black box, but at least as a tool for more complex modeling problems than just computing transport distances, right? And that'll be our objective for the rest of the tutorial today, is essentially, now that we've convinced you that this is something we can compute, how can we use it inside of larger pipelines, larger optimization problems, and so on to good effect? Okay, so today, I'll start by telling you some of the most basic applications of optimal transport, and then slowly we'll build and build and build and build and make more and more complex problems out of that, and of course end with some of the really heavy stuff that Marco will talk about at the end. So one of the big motivators for optimal transport in the computational world has been around, I'd say, for 20–30 years, is computing distances between histogram features, or bag of words, bag of just about anything. And so the basic application here is illustrated on this slide. So let's say that I have two photographs here. So we have Lombard Street, and some other street. The photograph on the left is bluish. The photograph on the right is reddish. And I could take these two photos and describe them as probability distributions over color space, right? So here, as you guys may know, there are lots of different spaces like RGB, HSV, XYZ, whatever, that all parameterize the set of colors and put some geometry on that space. Right? Basically, nearby colors are visually similar. And so now, well, we're in great shape for the optimal transport world, right? We have two histograms and some notion of ground distance underneath those histograms. And so what was proposed in 1998 was to compute a distance between images that's essentially the distance between, for example, their color histograms or histograms of different features. And so this is useful for applications like retrieval. For instance, I have a database of photographs and I'd like to find all the photos that have a similar look to the one that I just loaded. And so this is perhaps the simplest and most obvious application of transport, but it's a really strong idea, and somehow this idea, occurs and reoccurs in different, incarnations. So, one of the earliest applications, again, was to understand image processing. A couple years later in the computer vision community, things like SIF descriptors and SURF descriptors, which essentially are histograms over, some kind of edge or corner detector, became popular, and because there are histograms, of course, this was the natural distance to put on the space. And the most recent incarnation of this makes use of these really interesting embeddings from the deep learning world that, for example, can take a dictionary of words and embed it into Euclidean space. So if you can do that, how these people do that is still a mystery to me as a person outside of deep learning, which is amazing. But that aside, if you can do this in a meaningful fashion, then when you have a document, you can understand the document as a point cloud in that space, right? Where you essentially insert a point for every word in the document. Right? So now, all of a sudden, you have a histogram, which is sort of like an empirical distribution that describes two different documents. And then in this work, which of course they called the word movers distance, is essentially a measure of similarity of documents by measuring the similarity of those point clouds using the two Wasserstein distance. And I think they showed that it had some really great effect on the quality of these document retrieval tools. So like you guys can see, both of these, the image processing application and the one in sort of document retrieval here really don't require much more than just computing a transport distance, right? And maybe tools like the Sinkhorn algorithm that Marco talked to you before are very valuable because they can be parallelized over a lot of different histograms at the same time. And so for instance, if I'm searching a bunch of databases and have to compute, or a bunch of items in a database and have to compute a bunch of distances, then I could do that very quickly. But the really exciting development, I would say, starting obviously these numbers are very fuzzy, but starting in the sort of early 2010s, is that we began to think about optimal transport not just as a number that you compute that evaluates similarity, but as a meaningful objective term that can be incorporated into larger optimization problems that we care about in machine learning, as well as in other disciplines, computer vision, graphics, statistics, and so on. And of course, if you do that, right, if I start making some giant function f that has Wasserstein distance terms inside of it, well then, kind of by the chain rule, what I need is not just to compute the distance, but also to differentiate it. And hopefully now we've convinced you guys that we can do both of these things in a relatively efficient fashion. And so one of the really, really fun things about being a researcher in optimal transport today is that we have enough tools to get our hands dirty. And what this allows us to do is to start plugging in transport into different application areas and just play with what kind of effect it has. And so I'd like to propose to you guys today a new technical term, which is Wassersteinization, which is the idea of introducing optimal transport into an optimization or learning problem. And of course, we've had this pattern over the years with different notions of divergence and distance and so on, whether it's least squares, L1, kernels, deep nets, what have you. And what I'm going to try to argue to you today, and then hopefully Marco will continue to argue, is that optimal transport provides a really valuable and useful way to model that it's not just a distance, but in fact a useful objective term in a lot of different problems. So if we wanted to start with like maybe the world's most simple machine learning problem, one thing we might talk about would be averaging a bunch of data points, or maybe even more simply, averaging two things. Right? So let's say that I have a collection of histograms, or I guess in this case just a pair, and I ask for some notion of the average between them. Well, of course, there are a lot of different ways to average data, and if we take the average with respect to L2 or L1, or many other divergences, what you'll get is something like the image that we've seen on the top, which we've already seen at the beginning of the talk today. Right, so here I have a distribution nu, which is concentrated on the left-hand side, a distribution mu, which is concentrated on the right-hand side, and if I take their average algebraically, I just add them together and divide by 2. What I get is this purple distribution on the top, which of course sort of doesn't have the same properties as either of the two inputs, right? It has more peaks than either of the two inputs, and sort of it's bimodal, whereas the two of them, well, I guess I don't know if they're bimodal or not, but they're certainly more concentrated about a single point. So on the other hand, if we take the average with respect to the Wasserstein distance, right, we plug in optimal transport, we Wassersteinize our problem, what we see is that we get the average purple distribution on the bottom. Right, which is somehow a little bit more of a geometric notion of the average between two probability distributions, right? You can see that, in fact, the purple distribution here has probability where the two distributions are 0 in the input. And the idea is that when you're averaging, it's sort of sliding across the x-axis as opposed to just teleporting from one distribution to another. And this is a really powerful idea, both theoretically and practically, and it's one that can be extended in a number of ways. So this leads to a pretty natural problem of what you could call a barycenter. I think other people might know it as a weighted average, but essentially, let's say that I have a whole collection of probability distributions over space, and each distribution is given a weight. Right? Then these weights are positive, they sum up to 1. The one thing I could do would be to ask for the probability distribution that minimizes the sum of Wasserstein distances to all of the inputs. Notice when there are only 2 inputs, this is this averaging problem that I showed you before. And more generally, the Wasserstein barycenter is making use of the nice geometry that we have on the space of distributions under the transport metric. And so we have an illustration here to show you kind of what this looks like. So here, the three vertices of this triangle show three different distributions just over the real numbers. We're going to see higher dimensional examples, by the way, later. This is just easier to see. And the point that's moving here is showing the average, the weights that are used to average the three distributions in the corners. And we've compared on the right-hand side the weighted mean with respect to Wasserstein distance with the weighted mean with respect to L2. And you can see that the Wasserstein mean is sliding back and forth, that's really taking advantage of the transport maps that are getting computed behind the scenes. Whereas the L2 mean here, right, which is just literally, add them together with the weights prescribed using the triangle here, is just having mass kind of rise and drop back down. Right? It's much less interesting interpolation. Okay, so how can we compute this in practice? Well, in one dimension, in fact, how I prepared this figure was cheating a little bit, because remember, Marco gave you a formula for the 1D Wasserstein distance, and in fact, you can show that essentially by averaging quantile functions, you get this weighted average here. But more generally, what we can notice is that this is some example of a linear program. The first thing to note is that actually, even when your distributions are empirical distributions over like Euclidean space, you can actually write down a linear program that solves for the barycenter. But I think the more interesting case is the one that we'll explore here. So here, again, our unknown quantity, unlike what Marco has talked to you before, is not necessarily a transport matrix, the way that we've written it, but rather a distribution which minimizes the sum of Wasserstein distances to a bunch of distributions BI. And we'll talk about the finite case here. So this would be like histograms where your cost function is just some matrix. Okay, well, one thing that I could do is notice that this is kind of a complicated objective function as they go, because you're having a sum of a bunch of Wasserstein distances, each of which has to solve, some small linear program. And so one thing that I might do is expand it, right? So rather than having my unknown be just that unknown distribution A, I could introduce measure couplings P1 to Pn, which are essentially those unknown transport matrices for each of the individual transport problems that I have to solve from our unknown barycenter to the input distributions BI. And what I get is a ridiculously large linear program that's really hard to solve. Yeah? So this is probably not the most practical way to solve barycenter problems, but it's at least to argue to you guys that we can still reduce it to some linear program that we could solve in practice. Right? So here, what we've done is essentially replace our variable A with a bunch of measure couplings P, or transport matrices. But thankfully for us, there are much faster ways to solve this problem than to write essentially a generic linear program. And one of the first ones was proposed by Marco, actually, where essentially, remember that in the talk that we just heard, after you entropically regularize the optimal transport problem, suddenly it's differentiable in the input distributions. In fact, it's also convex, right? So one thing you can do is, rather than introducing a million transport matrices into your problem, if you're willing to regularize the individual optimal transport problems that essentially you need to compute the barycenter, then you can solve this problem just by gradient descent on the vector A of weights. So the A here is the barycenter. Right? So if you think about what this algorithm is doing, roughly, you have some hypothesis for what you think the barycenter is. You can compute the transport distance from A to each of the input distributions BI, compute the gradient from that, update A, and iterate. Right? And the nice thing here is that my number of variables is much more manageable. Right? And rather than having a bunch of transport matrices, I just have that vector of unknown weights. And this is enough to already see some really exciting and interesting examples of what the Wasserstein barycenter looks like. So here, Marco cooked up a data set, which was a bunch of probability distributions over the plane. Each distribution is composed of sort of 3 ellipses that are superposed in different shapes. I think they're just randomly generated. Now, if I compute the Wasserstein, or rather the L2 barycenter, right? So I just take all of these distributions, I sum them up, and I divide by n. This is what I get. And roughly, this is what you would expect to get, right? Because all of these different circles that we're averaging together are located in different places, right? So when I average them together, I have essentially an average of 1 million circles now, and it just looks like noise. Now, if you apply this primal descent algorithm that I just described for you, what we get is the Wasserstein barycenter, right? This is the distribution that minimizes the sum of Wasserstein distances to all the inputs. And one of the really amazing things that you get is an incredibly meaningful barycenter for this data set. Right, so remember that every point in our data set is a histogram composed of 3 ellipses that are all located in slightly different places. One is big, one is medium, and one is small. And somehow the barycenter perfectly describes this data set that you see here, 3 circles, one centered on the other. Yeah? And so this hopefully is already beginning to show you guys the power of the optimal transport as a kind of a lost term, right? That it's really fundamentally understanding the geometry of the underlying domain here, in this case just the plane, and incorporating that into the statistical calculations that you're trying to do. And of course, this application appears in all kinds of interesting places. One of them is in imaging. So for instance, let's say that I want to render a 3D model. And computer graphics people like me spend a lot of time worrying about an object called the BRDF. If you're not familiar with this, this is a probability distribution very roughly over the unit sphere, which is telling you essentially for 1 unit of light going into a surface, how that unit of light gets reflected back out as a distribution over the angles of the different reflectances. And people in computer graphics spend quite some time designing BRDF functions that represent different materials. So for instance, here we have a bunch of different brushed metals that I think are, well, I don't remember which BRDF they're sampled from. So the 4 corners here are 4 ground truth BRDFs, and then we can interpolate between them because they're probability distributions using optimal transport. And if you look really closely at this figure, you can see what happens if you use the Euclidean barycenter instead of the transport one. Namely, just look at the left column here. And what you'll see is that the upper left and the lower left both have 1 highlight, for example, on the cylinder. But those highlights are located in different places. And so when I average them together, what do I get? Well, I get 2 highlights, right? Essentially the superposition of these 2 things. Whereas if I use the optimal transport barycenter, you can see that the highlight kind of rotates from one into the other. Now, this particular figure was generated using entropic regularization. In fact, I think I had the entropy very high. And you can also see that in this figure because, what do you see? The corner distributions have a lot more black than the ones in between. So this same idea is applicable in a lot of different areas. Another one is in the processing of brain imaging data. So suppose that I have MEG or fMRI signals over the surface of the brain, right? So I give somebody a stimulus and a certain part of their brain lights up, and I do multiple trials of this experiment, that each of which shows more or less the same signal on the surface, but maybe they're slightly misaligned. Then you can imagine that the optimal transport barycenter is quite useful for averaging and understanding this type of data, because it can slide it along the surface of the brain to align it, rather than getting sort of essentially superposition all your data points where you're going to see the edges between them. Yeah? Another application that was recently proposed, essentially I'm just giving you a long laundry list of different applications of the barycenter, because once you can solve it, there's a lot of different places you can plug it in pretty easily. Another one that's in the sort of Bayesian machine learning world is in this Wasserstein posterior idea. So here, let's say that I have a very, very large data set. And I'd like to describe it using a graphical model or some other parameterized distribution that's hard to describe, right? And so if you're a Bayesian machine learning person, maybe rather than just extracting an MLE estimate of your parameters, you have some distribution over the likely parameters that explain your data, right? And so tools like Markov chain Monte Carlo, MCMC, essentially are sampling from this very complicated probability distribution over the parameters of your way of explaining your data. But let's say that your data set is so large it can't even fit on a single machine, right? Then one thing you could do would be to split it into j different pieces. And now I could run a Bayesian inference on each of those j pieces on j different computers, right? And under the assumption that my data is large enough, I wouldn't expect that these different j machines sample from very different distributions, but they're slightly different because they have different data sets. And so the big idea of the Wasserstein posterior is in parallel now, you have these j machines that are sampling from j different, slightly different Bayesian posterior distributions. And how do you think we merge them together? Well, we can merge them using optimal transport, right? Essentially by solving exactly the problem that I set out for you today. And so this is what they call aggregation. And one of the nice things is that this comes with some statistical guarantees. That like once if you merge together these posterior distributions, then in the right kind of limit, you really do get a nice unbiased estimate. Okay, so this is our simplest example of an optimization problem with Wasserstein terms, and now from here we can start building outward. So one thing that we proposed a few years ago was to study what we called the Wasserstein propagation problem. This appears in the semi-supervised learning world. So let's say that I have a social network, and every vertex of my social network is decorated with some histogram. Right? So maybe I collect somebody's behavior over the course of a year, you know, their spending, whatever, and I have this assumption that people that are friends tend to have similar histograms. Right? And this is sort of an ansatz that appears in a lot of different semi-supervised learning kind of setups. Then mathematically, what do I have? I have a graph where some vertices in a set S are decorated with histograms, and other vertices, the remaining ones, are missing. And my job is to figure out the missing histograms, or at least estimate them from the data that I have, under the assumption that it changes slowly along the graph. Well, essentially, we can extend the barycenter problem in a very simple fashion to this context, right? Where what I'm going to do is over every edge of my graph, I'll sum the transport distance between the histogram labels at the vertices. And this is some measure of the smoothness of an assignment of histogram as a function of where you are on the graph. And now if I minimize that function, this is what we call the propagation problem, and it gives you a semi-supervised model that allows you to, I guess, to impute the missing histogram data here. Notice that the Wasserstein barycenter problem is a special case of this one, where your graph is a star graph, right? So you have a star graph, and then all of the vertices on the outer spokes of the star are the input distributions, and the center one would be the unknown barycenter. Okay, so now let's continue adding more and more variables to our optimal transport problems, making them a little more complicated. And one thing that we can consider is a dictionary learning problem. So now, let's say that I have a whole collection of probability distributions, but I'd like to summarize them as kind of a linear space. Right? So in other words, I expect that there's some small collection of basis distributions that explains my data. Right? So here maybe I have a data set of 100, so we show you the first 3 and the last 3 distributions, which are roughly composed of some linear combination of 3 peaks. They're kind of Gaussian-like, but obviously very noisy. And now what I'd like is a basis of 3 probability distributions and weights that describe each of the data points bi as a linear combination of those 3. Well, roughly, we've already given you all of the tools that you need to solve this optimization problem, right? Notice here that, what are my unknowns? So my inputs are the distributions bi, that's like what's plotted underneath. The weights that describe bi are given by the lambda i's, right, for over all the k's. And my unknown basis is the set A. Right? This is an example of what we might call non-negative matrix factorization. And the really interesting thing here is rather than having a cost like KL or L2, these correspond to multiplicative and additive updates in the non-negative matrix factorization world, we can instead Wassersteinize our problem and say that we're going to pay an amount of money that's proportional to the Wasserstein distance between B and its approximation in the basis. And what we get is a really meaningful set of basis factors. So on the left-hand side, I show you the non-negative matrix factorization, in other words, the basis that I get if I solve the Wassersteinized version of dictionary learning. And on the right-hand side, it's with KL divergence. This, again, is what people call the multiplicative updates algorithm. And what you can see is that the Wasserstein barycenter, because it's allowed essentially to concentrate and move mass and slide it around along the x-axis, you get a much more meaningful set of basis vectors that are really explaining your data in a very intuitive fashion. So in that particular paper, it was applied, of course, not just to understanding histograms over a line, but in fact to very high-dimensional problems involving histograms that are topic modeling, right? So here I think they took a data set of documents, like similar to the word movers distance that discussed sports, and they want some basis that describes these histograms over the space of words. And what you get are things, you know, one basis which involves, you know, world and champion and race, another one that involves time, like on the upper right-hand side, and so on, right? So these are roughly just, you know, a small set of bases for topics that explain a very large dictionary of documents as input. Okay, so essentially so far I've given you guys a lot of different tools for averaging, right? We can compute the barycenter, somehow this propagation problem is the generalization of that. This dictionary learning problem is still some notion of, you know, trying to write one thing as a linear combination to another. A slightly more difficult problem, if we're following the usual hierarchy of challenging things in machine learning, is not just to compute means, but also to compute variances. Right? And of course, this leads in the statistical world to the problem of PCA. And one question you might ask is, can you Wassersteinize it? And of course, our answer is yes. Yeah? So this, when you talk about principal component analysis in optimal transport space, it's actually a little bit tricky to make this work. And the reason is that the space of probability distributions under the Wasserstein metric is a space of negative curvature. It's not flat. And so because of that, doing things like, linear algebra things like PCA is a little bit tricky. So one way to generalize PCA to this case is to realize that what PCA is doing is it's looking for one-dimensional subsets, like lines, along which your data is most of the variance can be explained. So if you want to Wassersteinize PCA, one thing you could do is say, well, what is a one-dimensional set? Well, it's just the shortest path between 2 points. It's a line. So if I have two distributions, mu1 and mu2, then I can understand the line between them as that displacement interpolation, right? This gives me a set of distributions, rho t. And so at the end of the day, I can say that each of my data points vi doesn't have to be, just close to a barycenter, but rather is close to that line from mu0 to mu1. And that gives sort of three variables, right? The t's for every data point, as well as the unknown distributions mu0 and mu1. And so here we see what you get when you do principal geodesic analysis in that space, right? So for instance, if you look at the 1 digits, you can see in the first column, it's explaining the rotation of the digit. In the second column, it's, I think, the width, like the thickness of the line. And I think the third one's already kind of noisy. So you get two meaningful components that already explain most of your data. Okay. So now let's talk about some inverse problems. So remember that in the dictionary learning problem, I wanted to learn a dictionary of distributions as well as a set of weights that explain all of my data points. Let's say that I have a dictionary, and now I have a new data point, and I'd like to write it as a combination of my dictionary elements. But rather than just a linear combination, like adding them together, I want to view that combination as a combination with respect to the Wasserstein distance. You can view this as an inverse problem, right? I want to explain an input histogram as some weighted barycenter of a dictionary of histograms, but the weights are unknown. And of course, once again, now that we know how to compute transport its derivatives, it's essentially a matter of the chain rule to solve this problem in practice, right, for these weights. And so what you can do is sort of explain every data point as a combination of the corners. And for example, you could apply that to reconstructing a volume. So here, let's say that I have a teddy bear and I punch a hole in it. My colleagues were not very kind to this teddy bear, but I'd like to restore the original geometry. One thing I could do would be to write it as a linear combination, or not really a linear combination, but a Wassersteinized combination of shapes in a database of complete teddy bears, and then use those weights to fill in the missing data. Right? And so essentially to compute the sort of closest point in that convex hull of teddy bears that I have in the Wasserstein distance. So if I do that, notice there's some kind of interesting features if you look closely at this teddy bear, that the input teddy bear, his legs are kind of skew, but my data set, all of the teddy bears have legs that are kind of on the same plane. So when you solve this problem, what you get as output is actually kind of an approximation of your input shape where it fixes the legs to project onto the space of teddy bears that you have. Perhaps a more serious application of this is in the brain mapping world, where maybe I have a new subject and I'm trying to write him in the space of brain images that I've already kind of carefully annotated and labeled and described. And so if I zoom in very closely, I can see the difference between using Wasserstein distances and using L1, L2. So on the left-hand side, we use sort of the Euclidean notion of barycentric weights. And if you look very closely, you can see that there's ghosting artifacts that roughly, because the different subjects in this experiment, maybe their brains are in slightly different locations, they've sloshed around or something, there are features in these images which are kind of spurious, right? Which just have to do with the misalignment of the images. Whereas if I try to explain a brain as a combination in Wasserstein space, you can see that we have like a nice smooth fold. But once again, you can also see some drawbacks of the computational techniques that we currently have on hand. Namely, the brain on the right-hand side is a little bit fuzzier, and that's what you pay when you use these entropic tools. Yeah? So finally, I'm going to very quickly describe two more applications of sort of Wassersteinized learning that I think are of interest to this community, but a little bit different from the last few that we've seen. One of them is in distributionally robust optimization. So let's say that I have a data set, and now I want to train like an SVM, do least squares, or whatever on top of that. But of course, there's an issue, which is that when I train my classifier, well, the classifier only has the data that I have on hand, right? It doesn't actually have the underlying distribution, which is determining the data that I'm sampling, right? This is a classic issue in machine learning. So in the distributionally robust optimization world, what they say is, can I optimize for a classifier that's going to be robust to perturbing my data set in a way that sort of gives nearby data sets with the assumption that somehow the empirical distribution, which is a sample of the actual data distribution that I want, is that those two objects are within epsilon distance in the Wasserstein distance sense. Right? So if that's the case, then what I'd like is, for example, a classifier that's robust to perturbing my data set as long as I do so without modifying the Wasserstein distance too much. And what you end up with is sort of a minimax gain style problem for solving this that we call distributionally robust optimization. And one of the really interesting things is that there are many, many cases in which this DRO problem is actually solvable using a finite convex program. And I'm going to refer you guys to the paper that's referenced here for details. It's a little bit long to cover in one day. But some of the really exciting and interesting advantages here are that there's some bounds on out-of-sample performance. So for example, because you're now just not only processing one data set, but sort of the space of all data sets within some Wasserstein epsilon ball of the one that you have, you get some nice performance that extrapolates outside of the data that you have, that there's some nice convergence properties, and something that's maybe a little bit surprising given that this is an infinite dimensional optimization problem the way that I've written it here, is that in a lot of special cases that we care about in machine learning, you can essentially work out the optimality conditions and see that it reduces to something finite. And then as one final application of sort of Wassersteinized machine learning, we can talk about transfer learning or domain adaptation. So here, let's say that I have two data sets. Like I have photos of products on Amazon.com, and these products are photoed on a nice white background, and they're very clean, and they have labels. And then I have photos on the shelves of a store, and I'd like to sort of transfer the labels from the photos that I have on Amazon to the photos I have on the store. But of course, the problem here is that these are two different data distributions. Right? There's the clean photographs and the noisy ones, and they're not the same. So in the transfer learning problem, what we can do is use optimal transport to align one data set with the other. Right? So here, at the lower left, like the blue and red points are maybe those Amazon photos with the nice labels. Well, under the assumption that they're sort of distributed similarly to the photos of products on shelves, I'll solve a transport problem to map onto that second set. And now I can push forward the labels of my labeled data set into this new space and train a classifier. And this has some very nice performance for optimal transport. So this is now a series of papers that started here. I think even at NIPS this year, there's now a paper. And essentially, there are all kinds of interesting extensions of this. For example, if I put some ansatz to make sure that the mapping T isn't too complicated, then this is a good way to make sure that you don't get anything too crazy. So with that, I think I'll hand it back off to Marco to wrap us up with some more problems.
Yeah, so I'll just continue with one very nice application that was proposed 2 years ago, actually at NIPS as well. And that problem is the problem of learning with a Wasserstein loss. Let me just give you just set up the problem first. Suppose you have a data set. Well, we are in a classic supervised inference setting where we have a data set of input and output pairs. And the input could be anything, but the output is pretty structured. It's vectors with non-negative values, basically count vectors. So a very, very natural example is the following. You have an image, and you have a set of labels. Or maybe you could have either a set or maybe a family with weights that tell you what are the most prominent objects here in the image. And the goal of this multi-label prediction problem is to find a mapping, f theta, from the image world to the set of, to those vectors that describe the frequency or the strength of each of those labels. And you want to basically use the classical supervised inference framework, which is just simply to minimize the sum of a loss between your prediction f theta of xi's and the ground truth yi. So if I just take one possible parameter theta, then I would just crunch that image and output a vector, f theta of xi, and that would be the vector of labels. And the question becomes very natural, is what kind of loss can I use here to compare what's on the left and on the right? And if you followed Justin's presentation, he mentioned very early here in this, the presentation in this session, that you could use something called the word movers distance to compare the set of labels on the left and on the right. There is, however, a small technical issue there, which is that very often when you describe images, you can pile up a long list of labels, and that doesn't make basically the label, each new label that you add up smaller because you have this normalization constraint. So somewhat one more natural perspective to look at those lists of labels is not so much probability distributions, but just histograms, count histograms. And so you would like to find a proper definition of optimal transport that allows you to compare two non-normalized histograms. And so right in 2015, several groups came up with a very similar idea, a very nice idea. And this is their proposal. What they said is, okay, if we step back from the original optimal transport problem, where we have to have this P matrix that fulfills those marginal constraints, can't we make things a bit more flexible by getting rid of those hard constraints and instead turning them into penalizations? And so the penalizer that they considered was the Kullback-Leibler divergence. But if you do carefully here, the Kullback-Leibler divergence is basically computed between the marginal of a table P and A plus the marginal of a table P, the column sum, and B. So somewhat, this formulation is a very natural generalization of optimal transfer between positive measures and not just probability measures. What is really nice is, of course, you can now use it on a point of clouds, and so you could use exactly that definition of an error, of a loss, to optimize your gradient, your parameter theta. But what is really, really nice about this modification is that it still allows you to use this very simple machinery of synchronous algorithm. So basically, the only thing that changes is a synchronous algorithm with slight modification in the exponent of a multiplier. So this I think, is one of the exciting fields for optimal transport. The way we have defined it so far, it was mostly restricted to probability distributions, that is, measures with the same total mass. With this modification, you can actually handle probability distributions with different total mass. So now the last part of the talk will be focused on this idea of generative models and how the Wasserstein distance can be useful to learn generative models. So let me just go to statistics 0.1. Since this is a tutorial, I would like to motivate the whole literature on generative models. So suppose we have data. We, as statisticians or people that like modeling or machine learners, we like to have a parametric family of densities to fit a density to that data. And the way we do it is just simply by gradually changing our parameters so that eventually we feel we have adjusted somewhat to our data. So somewhere, at some point, we feel comfortable we have found a good fit. And the right, I mean, not the right, but the traditional way to stop and to find for such a good fit was proposed by Fisher about 100 years ago when he defined maximum likelihood estimation. And so the whole engine of maximum likelihood estimation is to minimize this, to maximize the likelihood, which is equivalent to minimizes this sum of log of p thetas of xi's. So maximum likelihood estimation will look at the probability under one given model p theta of every point in your database, and then gradually try to increase it or minimize minus the log of p theta xi. There is one problem, however, with that formulation, which is obvious if you have to actually even encode it in your machine, is that because log of 0 is equal to minus infinity, there is a degeneracy there, right? So p theta has to be positive. Your family of densities p theta needs to be such that it's always positive at any point that you observe. Okay? Let me just say that this MLE procedure is very naturally interpreted in a geometric way as being a Kullback-Leibler projection of your data onto the set of densities that are parameterized by your model. So this seems to work well in 2 dimensions, but what happens when we have higher dimensions? So we cannot visualize much more than 3 dimensions. So this is a plot in 3 dimensions. Well, think for a second, what is the density in 3 dimensions? Well, it's a fairly big, complicated blob. And what we will do, if you want to do maximum likelihood, is basically fit that blob into the data. What happens when we have high dimensional data? So by high dimensional, I'm just thinking about images, for instance. An image is a point, is a vector living in dimension 30,000. So if you think about just even estimating a Gaussian in dimension 30,000, of course, this is completely hopeless. So what most people have been doing for a long time is finding low-dimensional representations for images and doing all of this machinery, the estimation machinery, in that low-dimensional space. The very nice point brought forward a couple of years ago by people that got interested in generative models is that we can instead view our problem differently. Rather than trying to fill up the space with a density p theta which is non-zero everywhere, what we might try to do is think about a latent space which is far lower dimensional, and then parameterize what we believe is this probability distribution on images using a push forward. And I'm taking again the vocabulary of Morse here. I'm going to take one low-dimensional probability distribution, send it through to the much higher data space, here the space of images, using a function that will map every point in my latent space. So maybe here it's a vector of dimension, let's say 100. And with f theta, generate an image. So I think everyone here at NIPS is familiar with those, with what kind of maps allow you to do this. But if you're not, well, you should know that there are some deconvolution architectures that allow you to map a vector, a low-dimensional vector, to something that looks like an image. Of course, if you just initialize your deconvolution net with parameter theta, which is not carefully selected, what you would generate most of the time is just some kind of noisy image. So the whole point of generative modeling is to find a parameter theta, and maybe a measure mu also if you want to keep that freedom, such that you are well approximating the data with that push forward. So remember again, the push forward definition is here, but I think you get the image by, you get the intuition that we are basically applying to each point of the base measure this map f theta, and then see what happens in the end. So the goal is to find a theta such that the push forward of mu under f theta fits the data. So you want to torture somewhat this manifold by changing the values of theta such that it fits well this. So one very classic, I mean, one very natural question that you should ask is, how can I measure the fit between that manifold, this push forward manifold, and the data? Well, if you just look at MLE, of course, you will run into the problem that I described earlier, which is that the log of p thetas of the, so here in MLE, we assume that p theta has a density everywhere, so this works. But if we just try to force p theta there with our parameterization f theta sharp mu, then of course this doesn't work because f theta sharp mu is actually 0 in most of the space there. So this doesn't work. And so we need a more flexible discrepancy function to compare new data and this push forward function. So I think the significant contribution in that field was proposed with the first generative adversarial network paper, which somewhat proposed a proxy to compute a discrepancy function between this blue manifold and the red manifold and the blue points. What it said is that if it's easy to classify points on the red manifold, giving them a label of 1, and points in the database giving them a label of -1, then it means that there's a very good split between the two. And so accuracy is somewhat measuring the notion of distance between those two sets. So if you want to find a good measure of discrepancy, you might as well find the best possible accuracy that a classifier can give you between those two sets. And that's what you want to minimize, you as the generator. You want to find a theta that will try to drive down as much as possible that maximal accuracy. There is, however, also a more straightforward maybe way to look at this problem, which is to directly define a notion of discrepancy between manifolds and points that is flexible and that allows you to compare measures with non-overlapping support. And I think at this point in the talk, you would probably guess that I will be advocating for Wasserstein distances or Kantorovich distances, as they're also known. And I would like to just make as a brief parenthesis that there exists actually a long body of work in statistics where people have said we should depart from maximum likelihood and consider other divergences. And so there's a funny title there, the minimum chi-square, not maximum likelihood, with an exclamation mark. And this was actually appearing in the Annals of Statistics. So this problem has been around for a while. But of course, this being a tutorial on optimal transport, what I will be interested in is taking for this discrepancy measure delta, the Wasserstein distance. And this was proposed a couple of years ago. So surprisingly, this is quite new. This was proposed in 2006, and people proposed this idea of minimum Kantorovich distance estimators. So it's exactly what I've been writing here. What they proposed there is you have a family, a parameterized family of measures. So they didn't really consider densities or anything. They were fairly general. And you want to minimize the Wasserstein distance between your data and p theta. So I don't really have a lot of time to explain the outburst of activity in this field, because most of the papers have been proposed in the last year. But let me just say that this proposal by Bassetti and al. Remained fairly theoretical for about 10 years. And then in the last year or so, we've seen a lot of very exciting proposals that try to minimize that Wasserstein distance between the data and the manifold. And as usual, as you would expect, the key problem there is to have a good way to approximate the Wasserstein distance, and not only the Wasserstein distance, but also its gradient. So a key way to approximate the gradient of this is to rely on the duality theory that we have explained a bit earlier. I will not go too much into details, but if you're interested, we will have a lot of talks on these subjects at the Optimal Transport and Machine Learning workshop, including by a talk by Léon Bautou, who will talk about Wasserstein GAN. So I would just like to conclude with some remarks. So I hope we have convinced you that there is a field out there in math called optimal transport. It's been investigated by the brightest minds in the last decades. It's a beautiful theory. It has some drawbacks from our point of view, because computation it's pretty hard. But I think we're making a lot of progress towards achieving the goal of just using transport as a black box somewhere in our algorithms. We have proposed a variety of applications. Maybe some of them were a bit fast, so you have to excuse us for not diving deep into the details. Also, if you have written a paper using optimal transport and we haven't actually quoted it here, please tell me, and I will try to add it to a set of slides that will be shared online. It's getting a bit difficult to keep track of all the recent applications, but of course, you're all very warmly invited to our workshop on OT and ML this Saturday. So I would like to just briefly say a few things that we could not talk about, and they might arise now in the questions. So the very nice thing about this theory is that if you like math, there's an almost infinite supply of very interesting math. I mean, there's lots of very nice books, a lot of very nice results. It's not clear that all of them will be useful for machine learning, but it's refreshing to see a field from math that can map very easily to machine learning in this way. There are a lot of statistical challenges to compute Wasserstein distances. So Francis Bach, actually, who is the chair of this session, will be giving a talk in our workshop as well, and he will be he will be talking in detail about this. And of course, when you say that there are statistical challenges, those challenges pop up when you try to apply directly Wasserstein distances. So this is a problem that we should be careful about, and we've put it here under the carpet. There's a very, very nice and exciting extension of optimal transport, which is, instead of comparing probability distributions, the machinery of optimal transport allows you to compare probabilistic metric spaces. So this looks a bit abstract, but let me just tell you that you can actually go above, and if transport is basically linear assignment, this concept of Gromov-Wasserstein is basically quadratic assignments. So there's lots of nice results, and we don't know yet how useful they will be in machine learning, but we had a paper at ICML last year that tried to use it. There was also a question on Wasserstein gradient flows. So this is also a field which is really, really very interesting, and which is basically the idea that, so if you know about gradient flows in Euclidean spaces, or for instance, proximal methods in Euclidean spaces, you're regularizing a function of a variable x with some squared Euclidean distance of x to the previous iteration. This is a prox operator. Well, it's very natural to do this computation in the space of probability distributions and replace the squared Euclidean distance with a Wasserstein term, and this is called a Wasserstein gradient flow. And this provides a very natural framework to do computations and optimization in the space of probability measures. And there's very deep links with PDEs there, and which are also reflected in a more dynamical perspective on optimal transport. And again, there's another new field that has was just created last year, which is how can we do optimal transport between not just point and metric spaces, but between more abstract things such as vectors and matrices, and parameterize transport in a more flexible way. So to sum up, if you visit this website, you will find first the slides for today's talk, and I am actually also sharing the keynote file. So if you want to use some of the animations or figures in some of your presentations, please feel free to use them. And there's also a survey that I mentioned that we wrote with Gabriel Perret, who's not here. He's the third guy who is actually responsible for a lot of the images here. So I would like to thank him for helping us set up this slides. And I would like to close this. So I think we'll have some questions. Thanks.
So I have a question. So can you deal with signed measures, with positive and negative
yeah,
weights?
so there's probably something I should have added it here. So there is the whole theory of Kantorovich-Rubinstein norms, which is basically when you are in the very specific case where you have p equals 1, then your Wasserstein distance becomes some norm in some sense. And then you can start adding extensions where you will relax some of the constraints on the total mass is the same or things like that. So you can there are some extensions. There is a path towards that.
In the first session, you guys had this image where you kind of morphed one shape into another using the geodesic.
Yes.
So is it true that if you have two closed manifolds and then you morph one into the other in the sense that you morph the the volume enclosed into one from the other, the surface that you get from geodesics is also smooth?
I think maybe Justin wants to answer this one.
Okay. As our
it's not working?
Oh, that's not. Okay. Yes, the question is if you interpolate between surfaces by viewing these level sets and then using this machine where you get a smooth surface in between. The answer is no. Pretty resoundingly no, in fact. So remember that transport wants to move mass along shortest paths. So effectively, think about this topological case where you've got one smooth surface that splits into two. There's going to be some point in time in which they tear apart. And right at that point, there's some singular issues that can
So
happen.
what I meant is that if you suppose you have a sphere, but you treat it not as a ball, not a sphere, and then you have another volume, like a closed manifold which encloses some volume, and you transport the volume along. So you like this. So hopefully the singularity, like the two-sphere case, doesn't actually occur.
You would hope that, but unfortunately, that's not the case.
Oh, really? Okay.
So I think something that's important to note here is that actually optimal transport is the right tool for interpolating shapes in a linear fashion. So if you have things that are aligned and you're moving it, then it makes sense. When you're talking about interpolating shapes geometrically, like you have some notion of elasticity, that is not what's going on in this problem. In fact, the Gromov-Wasserstein problem that Marco briefly mentioned at the end of the talk is a much better suited distance in that case. In fact, in that case, you can prove some nice theoretical results.
I see.
But of course, you replace linear programming with an NP-hard problem, so you win some, you lose some.
So like the original motivation for this question was this picture reminds me of Ricci flows. If you have a if you try to morph it into a ball or something.
Yeah,
so I don't know.
Definitely. So in another part of my life, I spend a lot of time working on things like Ricci flows, and this is not one of them.
Okay.
Yeah,
Cool,
but I'm
thanks.
happy to tell you more about that.
Sure.
Yeah.
Hey, thank you for your talk. My question is actually a follow-up. Are there connections to Riemannian geometry and optimal transport? Because it seems like there has been a lot of parallel development within Riemannian geometry where we're trying to find Barry centers and PGA and dictionary learning and so on. So
yes, so for instance, if you look at the Wasserstein PCA paper that we briefly mentioned, you will see that there are connections with geodesic PCA as proposed by Fletcher and other groups. The thing is, actually, space of probability distributions with the Wasserstein distance is not exactly a Riemannian manifold.
Right.
It's something that's a bit more complicated. It has infinite dimension.
Right.
It has a Riemannian structure. So, of course, there's some common flavors, but you can't actually directly use tools from Riemannian geometry in the Wasserstein space.
But are there special cases where you can approximate the space induced by the Wasserstein metric with like a Riemannian manifold?
Yeah.
Do you think so?
Yeah, I mean, roughly this Benamou-Bernier formulation is a Riemannian formulation. I understand there's technical issues.
Okay.
Yeah, so I don't know. I think Marco and I have different perspectives.
No.
But which is okay. I mean, from my perspective, intuitively, there is some manifold structure there, but you have to be careful how you talk about it, because it's not, like the boundary of this manifold is weird.
Right.
But if you think, so one thing that we didn't talk about very much today, which, like, if you go to MIT and you take my geometry processing class, we'll spend quite a lot of time on, is if you think about the set of distributions as itself, some manifold-like object, I won't call it a manifold, you could ask, what is the tangent space?
Exactly.
And the tangent space is somehow vector fields that advect around your distributions in a way that conserves mass. And it turns out that optimal transport is actually consistent with that under a very specific inner product, where roughly what you do is you take an inner product of vector fields now weighted by the distribution rho, and one thing you can show is that the displacement interpolation you get, like this interpolant that we showed a few times where you have distributions sliding along, is actually a geodesic. It follows, sorry, should be careful how I say this. You can optimize for using the geodesic equation. It's not quite a geodesic because this isn't quite a manifold, but there's some very close connection there.
All right, thanks.
Hi, nice talk. I have two questions. The first one is about the entropy recognition of the Watson distance. So imagine that we use this recognized distance for learning. So during the learning process, the original Watson distance will get smaller and smaller, but the recognizer term will be kind of keep the order 1. So do we need to tune the hyperparameter lambda to kind of make this two terms balanced during the learning?
Can you, so what two terms are you talking about? Sorry.
The first term is the original Watson distance term.
Okay.
So during the process, it will get smaller and smaller.
Yes,
because
yes.
you are learning, you are
Yes.
minimizing their distance.
Yes.
But the other term, the Q divergence between between your P and the inner product, the outer product of these two distributions will keep kind of order 1.
Yeah, so I think, so your question is when you use this regularized Wasserstein distance, you have a term which is transport, and then you have an entropic term, basically.
Yeah.
And when you want to minimize that quantity, this entropic term will pollute somewhat a bit your optimization.
Yeah,
and will be
especially
there.
when the Watson distance is very small, but the regularization term will be quite big.
Yeah, so you have an excellent point.
Yeah.
So it's true that this is a problem, and this is a problem that gets solved somewhat if you use this programmer hack, which is to directly auto-differentiate the cost of the Sinkhorn matrix that you get after, let's say, 200 iterations. Because in that case, what you're only differentiating is only the cost of what Sinkhorn achieves, whereas if you are differentiating the regularized formulation, you're also somewhat regularizing the differentiating with respect to this entropic term. So I hope this answers your question. So basically the Sinkhorn, what we call the Sinkhorn divergence, this idea that you just measure the cost of what Sinkhorn gives you, can be auto-differentiated, and it's actually fairly easy to do that, and you don't get this entropy somewhere disturbing you.
Can you imagine that if we kind of reducing the hyperparameter, the recognition parameter, the gamma, I think in your language, we reduce it, decrease it to 0, will it help? Kind of.
Yeah, of course it helps, but computationally it becomes harder.
Okay.
So the smaller the gamma is, the slower the convergence becomes. So there's a trade-off, basically. You might want to go for very, very small gamma, but you will need to do a lot more iterations to converge.
There are also some people that have considered some kind of interior point style, like start with a large coefficient and slowly shrink it.
Yeah, there's some nice work on Bernhard Schmitzer doing this kind of. There are lots of tricks now to drive this regularization down to 0 if you need to.
Okay.
Typically, you might need it if you are in a graphics setting or low-dimensional setting.
Okay, the second question is that you mentioned that for two continuous distributions, it's very difficult to compute its Watson distance, especially in high-dimensional space. So do you think it's an intrinsic difficult problem, or it's just we do not have nice tool right now, but it's kind of solvable?
Well, no, it's just a very standard statistical learning problem. You know, you're just solving an optimization problem. So maybe the easier way to do it would be in the dual. So you're maximizing the integral of f mu plus g nu. You have two dual potentials that satisfy some constraints. And you're doing this with finite sample data, so you have to regularize no matter what. I mean, there's no way if you use directly the optimal solution that you get from data, then it won't look anything like the solution that you would get from the continuous distributions. The question is, how should you regularize it? It's not clear yet. There are many approaches. I mean, there are very few approaches that have been proposed, maybe one. But I don't think it's intrinsically very difficult. It's just a standard statistical learning problem, but we haven't yet found some maybe satisfactory solutions.
Okay, thanks. Okay, hello. Thanks for your nice talk. And I have one question. You know that the optimal transport distance is a more accurate distance than the sinkhorn distance. So there's a difference between the optimal transport distance and the sinkhorn distance. So according to the definition of the sinkhorn distance, we can have a very trivial bound on the difference between them. So do you have an existing result about the difference? Do you have a bound on it?
Yeah, so this is a very good question. So I didn't detail this. It's a bit of a technical point, but when you run the sinkhorn algorithm, you will get a transport matrix after, let's say, 10,000 iterations. Your transport matrix increasingly looks like a matrix that has the right marginals, but still it doesn't have them yet, right? Because actually sinkhorn converges when you found a matrix that has the right marginals. Okay, so in the primal, you get a solution that's not feasible, but you get something that is getting close.
Yeah.
In the dual, however, if you look at the dual optimal, the dual regularized problem, the solutions that you get are always feasible. So this always gives you a lower bound on the actual Wasserstein distance. Now, in a paper at NIPS this year, proposed by, it's one of the papers that I quoted. I think, I don't want to,
yeah,
the name is Althusser.
About it.
It's about Philippe Rigolet's group at MIT. There's a paper at NIPS this year called Green Corn Algorithm.
Sorry?
It's Philippe Rigolet group at MIT.
Yeah.
And they have a paper called Green Corn, like greedy sinkhorn. And then they propose a way to basically project the result of the sinkhorn algorithm to the polytope of constraints. And that what basically this gives you is an upper bound and a lower bound, a rigorous upper bound and lower bound on the Wasserstein distance. So yes, you can get one almost for free.
Yeah, okay, thank you very much.
And of course it's true that like if you take the limit as gamma goes to 0, that you really do recover.
Yeah.
Right, and I think there are some bounds on the convergence rate of that.
Yeah. And so just to say this last comment, it's usually much easier to recover the Wasserstein distance than to recover the actual optimal transport plan. Okay. So if you just look at the Wasserstein and just the value of the objective, when you let gamma go to 0, you will very quickly converge to the true Wasserstein distance. So I'm not very worried about this. What is much harder actually is to converge to the argmin, to the actual optimal transport.
Okay, thank
Hi,
you.
optimal transport is for a predefined metric, but we also have problems that we want to transfer between two totally different domains and we don't have any metric. For example, we have two languages and we want to learn a bilingual dictionary. And still we want to regularize the transfer functions not being arbitrarily complex. So can we use techniques from optimal transport for that scenario?
Yeah, so that's a very good question. So actually, maybe I should have put a line on the slide. So for instance, last year there was the supervised word movers distance where they were trying to find basically learn a metric. I also had a paper a few years ago called ground metric learning, so it was trying to do a bit the same thing, trying to learn the metric. And if you look at the applications of optimal transport in GANs, it's also clear that learning a metric somewhat is important to achieve good performance. So yes, learning the metric is one big problem in optimal transport.
Like I think you're also asking about two distributions over two
different
spaces. And this tool that we talked about, this Gromov.
Oh yes. Then in that case, you might want to look at Gromov Wasserstein because it's also a very interesting extension that handles the case where you're comparing distributions which live in completely different spaces that you cannot actually compare. So. If you just look at that paper, if you just Google Gromov Wasserstein, you will see how you can compare probability distributions living in different spaces. Each of those spaces is endowed with a metric, and this is enough to define a notion of optimal transport.
Okay, thank you. You just mentioned to learn the metric.
Yes.
What are the...
Well, you typically set a prescribed family of distances that you think are meaningful, and then with respect to some criterion, you will try to find a good metric that works for some criterion.
Okay,
So it's just a typical machine learning perspective.
Thank you.
It's, if you look at metric learning, there's a whole literature on metric learning in the years 2006, 2012, where people were optimizing metrics. And this is a natural extension of that.
Combine these two, like learning a metric and meanwhile...
Oh, of course, you need to have additional information. I mean, you can't just say that you're going to learn a metric without some criterion. So you have to define some criterion that helps you navigate and find a good metric.
Thank you.
Thanks for the tutorial. So my question is, after estimating the transport map between two probability distribution, what are the scenarios you can actually evaluate the actual probability density after the transport? So,
You mean, do you get the push forward measure?
yeah.
If you give me well, this is a change of variable formula. So the problem is computing determinants of Jacobians.
Yeah, so I can see if it's an invertible mapping between two distributions, so it's easy to evaluate. But I mean, I'm just curious, what are the exclusive list of?
I think there's sort of two approaches, right? So one would be, if you solve Sinkhorn or any of these other techniques, then you really do solve for a transport matrix. I mean, maybe it's factored a particular way, in which case, essentially transferring distributions is just a question of, like, the push forward is just matrix multiplication. The other case, this Monge problem where you really expect it to be a map, it's much, much harder. And I think people in the kind of numerical partial differential equations world, like Adam Oberman and company, have tools for solving the Monge pair equation, which is the PDE that kind of governs what's going on behind the scenes for that map. But the computational methods there, I think, are much more specialized and require a lot of very careful treatment.
For me, I can only see, like, if those two distributions are Gaussian, it's very easy to evaluate that. But
well, there's one really interesting compromise. I mean, if you look at that transfer learning paper, the domain adaptation, what they do is they add assumptions on the structure of the transport map. So they say, like, optimize in the space of transport maps with this form. Mm-hmm. So they no longer are solving exactly optimal transport, but the trade-off is that they get a map that they can more easily evaluate and understand, right? So I think that's kind of an interesting alternative that maybe is worth exploring a little more.
Okay, thanks a lot.
So it seems we have to take questions offline now because the room will be used by the next tutorial. So if you have questions, you can of course come and talk to us. Thank you very much.